Hello, good morning, everyone. Welcome to this session on the Onward paper session. So I'll be sharing this session. My name is Vasconcelos. There will be three exciting talks, and the first one is What You See is What It Does by Egan Meng. And please.
Can you hear me?
Oops.
Good morning. Thanks so much for joining me today. I'd like to motivate this work a little bit. My name is Egan Meng, and together with Daniel Jackson, we're at the software design group at MIT. A lot of this work is about trying to understand how it is that we collaborate with both LLMs and people and to have a little bit of agency. And we're using some of these lessons to teach a course, the software design course. So I'd like to start by thinking about some of the motivations for a vision for software, not just for today, but also for tomorrow. One potentially contentious point is LLMs will continue to get better. I think this, depends on the degree, but a slightly less contentious point is our applications are going to grow a lot more complex. Now, the point here is that these are moving targets, that the need to collaborate in some shape or form will remain. And so what does it mean to work towards a structure for software that scales with advancement, no matter how much progress is made, no matter how complex things get? And so I'd like us today to think a little bit about the future of that collaboration and what are the properties that we like from that collaboration. So here are some of the goals that we've been thinking about for this shared vision. First being confidence. The idea here, the aspiration is contributing without fear, that you can make a change and it doesn't actually break anything, and the threats obviously being what we're very familiar with. The other goal is one that's a little bit more vague, but it's this idea of creativity, that you have the freedom to freely express new and interesting behaviors, that you're not sort of constrained by how tightly coupled things are. And the third is one of clarity. It's one that we should be able to ask the questions that interest us and find some sort of provenance to be able to trace it back to the source. So this talk is going to be about approaching these goals through a series of steps. And so working backwards, what properties of the software do we need to achieve this? Those are properties of the collaboration that we think are desirable. And our answer to that is this notion of legibility. And to achieve this, we'll introduce a structure that's made up of concepts and synchronizations, and we'll dive into that today. So the building blocks of software. We contend that there are these things called concepts. A very common way to structure applications these days might be something like an object, and in particular one that's very common might be a user object. So what might be some state associated with it? Now, for example, we have a name, maybe have some sort of email, perhaps a profile image or an avatar, some password, and some notion of logging in a session or a token. You might implement this in sort of an object-oriented way using a user class and associate all these different states with it and behaviors in terms of methods. And the question is this a good building block? Is this something that we think is a good foundation to rest the rest of our software on and to iterate on it over time? I would contend that there are multiple concerns here and multiple reasons to be concerned. For example, in terms of reusability, this is a rather specific combination of features. You can imagine applications that don't have some sort of login requirement, or others that don't have some sort of notion of profile or an avatar. The other is breakage. Imagine that you're relying on some kind of database for your session management, it goes down, and now you can't access avatars from, let's say, your public site. And finally, it's this notion of evolution, where the requirements do change over time. And as you change each individual piece, how does that reflect on the rest of the software? Does it mean that you have to tread really carefully to make sure things don't break? So taking a step back and thinking about the etymology of concern, it's actually kind of fun. So you have the with or together, but I'm not sure how to pronounce this. Carnera, I believe. It's this notion of to sift, to perceive or comprehend, to discriminate or distinguish. And the idea behind a concern being to perceive an individual aspect from the whole. And I find that rather appealing. I think it's interesting to think about how we might extract a concern from a fairly conflated set of behaviors such as this user class. Now, one, we might say that the first two states are part of some identifying concern. There are many ways to potentially uniquely identify an individual, and this is usually why the state requires a condition for uniqueness. But there might be more, maybe more than just name and email, maybe a phone number in certain applications. Then you might have a concern of some notion of a profile, not just the avatar, but some sort of biography or some other descriptive pieces of state. And then a notion of some sort of authentication. Could be passwords, could be passkeys, biometrics. And finally, any sort of notion of a session and logging in. So I would contend that these are the essence of the individual timelines, so to speak, of behavior that we do care about. And they're kind of grouped together and evolve on their own. So this is, in one way, a way to phrase what we think of as concept design. That concepts are these building blocks for software that embody concerns. They're described by specification, and the first part of it being a purpose. This is the concern that you're addressing, the problem that you're solving, the reason for this concept that you've specified. Then there's the principle. This is a little bit like a canonical scenario, like a test case. It's how that concern typically plays out and why that these behaviors, these informational updates actually satisfies the purpose that you laid out. Then you have the state, and this is a set of relations that pertain only to what you need for the concern, no more. And finally, actions, which are simply some behavior, a set of functions that update that state. And so one way to think about this is a concept is something like a state machine for a single concern. It describes its behavior over time, and it captures just the amount of state it needs to figure out what it needs to do. So an example, let's take our authenticating concept. Its purpose, ensuring that user matches what they claim in terms of identity. And a principle is fairly straightforward in this case. After registration, they can verify their identity by, let's say, a password. And you'll note that the state is simply just one line. It is one relation. The syntax here is modeled after Alloy. But the more important part is that we're just noting that it's a connection between user and some password string. By the way, the bracketed user at the top is our way of denoting some sort of generic import. You can think of this in practice as like a UUID. We're not claiming anything about the actual type of the user or the structure of its information. We're just saying there's some generic thing that's called a user. And finally, the actions that you might expect, a registration and a check. And together, this authenticating concern kind of describes how a notion of password gets registered and how it changes over time and how we can check that it matches what people claim they are. One important point, and often a point of conflation, is that concept design is somewhat orthogonal to object-oriented programming. You can do both in each. So these are examples of just regular TypeScript objects and classes that are implementing concepts. And the key distinction here is that object orientation, in our view, is more about sort of the form, the structure. It's in the name. It's about objects and orientation around them. And while there are allusions to, let's say, entities in the real world that we can map sort of semantic notions on top of, it doesn't prescribe very strongly like what you should put in state and what kinds of actions should be related to methods. Whereas concept design is all about the function. It's about what is the purpose, right? We're telling you it's as part of the definition, you need to specify some semantic notion of importance and a principle and how it evolves over time. So there's some synergy here, and there's also orthogonality. So we've been here before. There's been many attempts at trying to structure more semantically relevant groupings for our software structures. Some like role-oriented programming, aspect-oriented. This might be seen a little reminiscent of entity component systems, heavily used in game engines and intensive 3D workflows. So what's new? One of the central contributions of the paper is thinking about this notion of putting things together. It might be okay to have some nicely oriented, separated concerns and classes, and maybe you did it well, but where's the challenge? So let's think about some patterns of composing these concerns. Suppose we consider each concept as some sort of microservice. It's just floating in the cloud, operating, you can stand them up on their own. And then the first pattern might be just let loose, allow all interdependencies. right? I like to call this the hairball. It kind of looks like this. And I would contend this doesn't spark joy. If you look at this, my confidence is going down. I don't know if I can change one thing, if there's a race condition somewhere else. Creativity is way down. I don't want to add to this thing. This is a liability to maintain this. And I mean, clarity, just look at it. So another pattern that is common is this notion of, let's have some order, let's route. Suppose we have some sort of client, it interfaces with an API gateway of sorts, and then we're going to let the gateway manage each individual concept, the microservice, independently. And we'll pray that the concepts don't actually talk to one another, or the microservices don't talk to one another. So this seems well organized. What might be some complications? Let's take a step back and think about a typical social media application. Imagine that while the post appears, some new post has been created, and let's think about what happened right before it. What are some of the preconditions, right? Did we require a user to be logged in to create that post? What about the preceding actions? What led directly to that post? Beyond just they clicked a button on a page, it could be the case that, let's say for your site, uploading an image automatically generates a post. What happens after? So a post has been created. What are the behaviors that you want happen in your application? Well, first for the post condition, you want to post that, you want to persist that. And then succeeding actions, maybe something like we want all the followers of the poster to be notified. These are just some examples of perhaps desirable behaviors that you might want to configure and implement in your application. Let's take a look at how you might do this using that route pattern that we saw before. So this is just some notation from Node.js's Express server, but imagine you're setting up a route for a post request to post / some sort of user ID. And our first concern, again, thinking in terms of concerns and concepts, is, well, checking if they're logged in, some notion of a session. And if they are, we're going to do post.new. And then we want that kind of succeeding action, right? Get all the followers of this user who made a post. For each follower, let's notify them. All right, what if we wanted to have a different kind of pre-action or preceding action? What does that mean? So in the example of an image has been created, let's make an automatic post out of that. Well, we're gonna have to start somewhere else, perhaps. There might be a different route for image uploads. The image is created, and then this is where we say, okay, let's make that automatic post after the image creation. Now, you might see the problem, which is we have all this logic that we want happen, right? We want all the posts to be automatically notify the followers. So we're gonna have to repeat that. So we have following for each follower, notification. That might be okay for just 2 routes. And then let's say over time you say, hey, let's introduce some more behavior. Let's add recommendations. And for each post, we're gonna have to update or re-index the recommendation algorithm. So we'll add that over here, and then don't forget, you're gonna have to do that over here. This is a common pattern, and in many of the case studies that we looked through for the paper, we saw this replicated multiple times. And more importantly, what does it say about those desirable properties that we had, right? Is this confidence inspiring? Suppose your following microservice goes down, and now it seems to affect your ability to update your algorithm, even though it's orthogonal. What about creativity? We wanted to add this kind of unilateral function on top of new post creation, but we had to track down multiple places in which post creation was happening. And finally, clarity. Can you easily spot all those behaviors we're talking about, the preconditions, the preceding actions, all those, the before and afters of post new, from reading this code? So if we were to extract that, it might look a little bit like this. Here is the little bit about just normal authentication or through a session of some creation of a post. Here is that automatic creation of a post after an image. Now here is the concern about the whole following behavior. And this final bit is about the recommendation. And notice that it's actually just jumping across, right? It's really just dependent on the creation of the post to update algorithms. This is the essence of what we call synchronizations. What if we could just extract those and say, this is what we want to have happen? Here's what the syntax might look like. For the very basic one, the user post, suppose we consider the request coming in through that express handler as its own concept that encapsulates all the HTTP, all the other side effects, but basically says there's this action trace that request user post. So when that happens, Let's check through the session that they're logged in, and let's make a post. This is how we declare behavior as a synchronization. And then the same thing for the image post. So when a new request for an image has been made and the image has been created, notice the two conditions inside the when clause here, then we create a post. And so to break that apart, what we're saying is that in this structure for synchronizations, the when keyword says, here are the preceding actions. Here are the triggers for this behavior that I want to occur. The where is, here are the preconditions on state. Here's the information that I think is relevant. And then the then is, here's all the succeeding actions that should happen. And that's it. Those are the only three keywords for synchronization. Importantly, note that we don't have this notion of explicit execution flow that kind of partitions the space into two route handlers. Both of these lead to one node, which is just post creation. What that means is for all that behavior that we said coming after, we can hook onto it. So the notify followers becomes a one-time declaration. When a post is created, find the followers of the user, notify them. Same thing for the recommendation update. And so in this way, by factoring out this kind of structure, we can kind of compose these concepts that are granular. They're declarative in the sense that they're not actually immediately calling them. They're saying this is what should be happening, right? And there's no duplication of that logic that we saw with that route, the route solution. So what does the implementation actually look like? It turns out to be quite simple. These three boxes on the top right, you can think of these each as like a concept microservice. They encapsulate whatever persistent store that you might use, a runtime, doesn't have to be node, and its main point of contact, they don't talk to one another, is through some intermediate engine, kind of like the Meteor pattern from Kevin Sullivan, or just this notion of like an event-driven store. So they communicate action records as simple JSON structures. And then synchronizations are also data. They're just these patterns with the when, where, and then clause saved as JSON and then registered with the engine. And the engine itself is not a framework, it is just a library that you can run in whatever deployment structure that you'd like. So what does a very basic concept look like? This is an engine that we did in TypeScript. It is any TypeScript class. All the methods are considered actions except for those with an underscore. So these are not recorded, and you have some sort of state. And the only requirement is that all your actions need to take in sort of a named record. So no positional arguments, just give it a record, a map of the key values that you want. And then a synchronization in TypeScript looks a little bit like this. So this is one that says, when a post has been deleted, find all the comments who have that target. So basically all the comments of that post, then delete all those comments. This is an invariant keeping synchronization to make sure you don't have any dangling comments. And you'll note that this returns just that data structure. It's a record with these when, where, and then keys. So let's talk about this notion of legibility that I talked about in the beginning, which is how do we understand the system that we're building up? Now, you can kind of think of these things as sort of these two layers. The concepts are these individual concerns. Here are some concerns that are fairly normal for social media apps, like notifying, friending. And here's some synchronizations about behaviors that you might expect it to be to have. And there's this property of integrity where there's no notion of some sort of horizontal flow of information between the concepts, right? Note that they don't know about one another, they can't import each other, and neither can the synchronizations. So they're always kind of in these vertical slices. Let's say you add a new concept. You say, okay, we have a recording concept, and every time a lecture has been recorded, we want it to post. This can be done in an incremental fashion. You don't have to think about integrating with an existing web of microservices, but rather you just simply need to add your concept anywhere and then say, here are some behaviors that you declare through synchronizations that you'd like it to compose with the rest of your system. And finally, the notion of transparency, which is what we were exploring with this idea of thinking about the before and the after of a post, that there's a specific place to look for preconditions on information, that's all in the where clause, and the preceding actions, which are all in the when clause. And because that's the only mechanism by which the system evolves, you have a guarantee that this is exactly where an invocation was called. Like if you want to look for how post.new happens, just search through all your synchronizations and see if it shows up in a then clause. we like to think of these three properties together as this notion of legible software, the ability to kind of read your software and understand it, to have a little bit of confidence about what's going on. And so we think these properties of the software lead to some of those properties that we talked about, our goals for collaboration. Now, namely, if you have this integrity, you might have a little bit more confidence that when you add pieces, it doesn't break the others by construction. Perhaps in terms of incrementality, if you feel like you can always just add one more thing, one more concept, one more synchronization, perhaps that leads to a little bit more creativity without restraint. You're not being hampered. And then this notion of transparency being a form of clarity, to be able to trace what is going on and ask questions that pertain to your system. There are, of course, drawbacks to any approach. We are very aggressive about this decoupling. So the decoupling of concepts, the positive is that they're fully independent. The negative is this thin straw in which they must talk to one another. There's no RPC, they don't know about types. It has to be some serializable JSON structure. The decoupling of synchronizations, it's nice that they don't have this property of context dependency. If you read through a route handler and you see post.new, it's actually pretty context dependent, right? You got to look up and see, okay, under what handler is this occurring from? How does this actually, what are the effects? Whereas synchronization will declare in the when and the where before that exactly what's going on. That said, that means duplicating all the conditions. So every time, it's not duplicating the logic, it's duplicating the context for every piece of action in the system. And who knows if that's a good thing or a bad thing. So this is a vision that we're thinking about in terms of evolving software together in a collaborative fashion, about concepts being a language for function. They're structured around individual concerns. They're in terms of these familiar shared terms of behavior, and that perhaps they can be constructed as a collective effort to evolve slowly, to be battle tested and shared amongst multiple applications, not have individuals redo the same user concept many, many times. At the same time, the synchronizations offer that kind of domain-specific configuration, the value that you want, the specific configuration of familiar concepts and the needs of your application. And we think this would be a targeted effort, that this evolves quickly. So a set of concepts like these with karma thread posting might create something like a Hacker News clone, which is something we've done before. So ultimately, taking a step back, what we're excited for, we're not actually super excited about kind of a new structure or implementation or even like a specific way of doing the software. We're more excited about this idea of this collaboration that can inspire confidence, creativity, clarity, right? That software will be legible to everyone it affects. And perhaps, maybe one day, that what you see is what it actually does. Thanks so much.
So we have plenty of time for questions.
I love the aim of the confidence, the legibility, all of us, I'm sure. You spoke about some case studies. Can you go a little, tell us a bit more? And in particular, in those case studies, have you compared with the competition, for instance, with aspect-oriented programming or earlier approaches also developed at MIT?
That's a really good question, thank you. So in the paper, we mostly explored this, there's a picture of it, something called the real world benchmark. This is actually a pretty fun benchmark if you've heard of it. It's purporting to be the mother of all demo apps. It's kind of like a Medium clone, like a social media app with a lot of blog posts. And the interesting thing is this was kind of like a developer organized effort. So there are hundreds of implementations across many different languages, a lot of esoteric ones as well, all implementing the same app. So what we did was we also implemented our own version. We did some not comprehensive, but basic studies on sort of like an industry perspective. So no, unfortunately, we didn't have sort of strong comparisons against like aspect-oriented programming and perhaps more of the other higher level approaches, but we mainly focused our efforts on comparing on, well, how do people do it in software practice today and looking at those details.
Thanks for your talk, Jonathan Aldrich from Carnegie Mellon. I've been a longtime fan of concepts, so it's great to see that you're working on, how you can make them a part of building software. So I really enjoyed your talk. I think the first sort of concern that comes to my mind about this is the synchronization part, and I wonder about scalability, right? Because synchronization is about the interaction, which is always the hard part in software, and especially when you think about concerns, right? This was a challenge in aspect-oriented programming too. You separate the concerns, but how do they integrate? And so I wonder, as you add more concerns, does the synchronization between them kind of, does it turn into a quadratic kind of thing, right? Where each concern needs more constraints in the sync part, in the sync that that accounts for it to mediate between others. It's an empirical question, perhaps, but I wonder if you have any insight about this issue.
That's a wonderful question. Thank you so much. That is essentially the primary goal of this entire research project. We had an interesting notion of concepts, but we've always struggled with how to actually compose them. Previous versions of a class were done on top of this routing pattern, and it had all these problems of it didn't scale, right? We had to track down, okay, all these concepts, the concerns are everywhere, how do we actually merge them? And so this is experimental. It seems hopeful, but there's a lot more details I was not able to get to during the talk about some notions we developed of an execution flow, about a notion of how to group actions. And it turns out that it's very powerful and distinguishes this from a traditional event-driven system and reactive system because we have a notion of what it means to have multiple conditions in the preceding actions. It may seem strange, like if you condition on like a request and like a user signing in, well, there are thousands of users doing both at the same time. How do you group that? And our particular notion of a flow that groups that seems to cut through these concerns pretty well. Obviously, there's so much more to do and think about other cases, but it seems pretty hopeful that we've found essentially a language. That's why we centered around these three keywords of trying to be like, if we can describe that behavior, we should be able to put it in just that much text.
Yeah, thanks for the cool talk. I was wondering if you could talk a bit more about the class. So like, are the students using, how many students do you have? What level? Are they using your language? And also I'm curious, like, are they doing one project through the whole quarter? How are you guys, how's this class working?
Yeah, the class is going right now, and it's a source of a lot of fun and stress. But essentially, they are going to be using this pattern, and they're starting to integrate it already. The class is really structured into two projects, a personal project and kind of like a group project, and we'll see how they do on sort of both. We're interested in the ideas of actually having reuse of concepts between multiple people, see how that pans out. But we're also doing all sorts of other things in the class, like welcoming students using LLMs. And yeah, it's an ongoing story, and we'll have much more to report on next spring.
Cool, thanks so much.
So are there any further questions? Okay, then should thank the speaker.
Thank you so much.
You're talking next? Yep. So you're planning for speaking for a long?
Oh, sorry? Speaking for a long time?
Yeah, so you have an half an hour, but your plan is to speak for what, 20,
I have
25?
a demo, so I can
The second talk of this session is Literate Tracing by Matthew Sotos. That's how you
You can say, I actually don't know the proper pronunciation. Satuda, you can say Satuda. Yeah, I think Sotuda is the
Sotuda.
Sotude. Sotude, let's establish that.
Okay, Sorry about that. And
No worries.
please go ahead.
Cool. Okay, so the motivation for this talk is actually kind of similar to a lot of stuff we've been hearing about, so I'll just go through it quickly. I kind of like to start with some excerpts, my sort of favorite 3 sentences from the GNU Manifesto. So he says, a user who needs, this is like the dream, right? A user who needs changes in the system will always be free to make them. Users will no longer be at the mercy of one programmer or company which owns the sources and is in sole position to make changes. Schools will be able to provide a much more educational environment by encouraging students to study and improve the system code. I think the last one is even maybe my favorite of the 3. Yet, it's 2025, and we have so much free software. This is a free document viewer, Firefox, we have all of this stuff. But the thought of sort of casually studying and customizing this software, for me, kind of fills me with a kind of embarrassing amount of dread over this thought. And I think the answer is something that we've heard again and again and again through Onward the last 2 days, and that's complexity, right? So if we look at kind of, lines of code counts, I'm sure everybody here will tell me are not a good measure of complexity, but it gives you some sense, right? All these major projects we're using every day, it's, million+ lines of code. And this is kind of what fills me with fear of even getting started in reading some of these software. And I think there's a hope, I've at least always had this hope, that something like the STEPS project is gonna work out, and somebody's gonna invent just the right level of abstraction or kind of tower of languages that we're gonna have, my whole Linux desktop environment in 20,000 lines of code, right? And I think what I've sort of slowly come to believe or accept is that this is not really gonna happen. So users have a lot of righteous demands. They want their software to work the way that it's been working, right? I want Vim. I want my key binding set up. I want my Vim script set up. And so just trying to use any kind of new rewrite of the software is already a hard sell. And on top of that, I think a lot of the complexity in modern software is essential, right? I mean, I think even you just try to, for a kernel, for example, even just trying to write, some driver software for some tiny, ADC chip or something, you got to go through the manual, and there's all this crazy, first you do this, then that, and everything. And so users want all these different combinations of hardware, software configurations, high performance, security, and reliability, and all of that stuff. I think we're sort of, at the end of the day, stuck with having some of our most important software be kind of incredibly complex in this sense. So the question is, if I accept that situation, what to do about it? And the point of this talk is to tell you about one experiment I've been doing for a couple months now and how it's kind of worked out for me. And that experiment is about documentation. So basically the pitch here is that documentation can help make software more understandable, and we can use tools to write slightly better documentation in this sense. So I guess I don't really need to go through these 2 slides, but without documentation, everybody who wants to start learning about how Firefox works or whatever has to do it on their own, right? But the magic of documentation is that whoever figures it out first, whoever spends a few days understanding, how Vim stores lines or whatever, can write documentation after they've learned it and then share it with everyone else, and they can benefit from that knowledge, right? Okay, so basically writing is nice. Writing lets you share what you have learned with others. In practice, right, documentation is used all the time by programmers. And in my sort of mental model of the world, there are 2 styles of documentation that people use. The first is comments, okay? And so comments, in my opinion, are great because they're directly tied to the code. It's like, yes, here is where the current line is set, right here in this code, and this is why. But of course, there are some bad things with comments. One is that, most of us write code in just ASCII text. And so it's very difficult to put real diagrams in there. Sometimes you load up some kernel header and you've got like a whole, ASCII art diagram somebody spent like 1 million years designing, but this is kind of painful, right? And the other bad thing about it that's maybe more fundamental is because those comments are at a particular location in the code, it's very difficult to give a more global insight of what this code is doing. Comments are really about this chunk of code. So sort of the total mirror of comments is out-of-band documentation. So this is like a design doc or something. And these design docs are great because it can explain the global context, right? If people haven't seen it, you can go online and see like architecture of open source applications, you know. It explains the whole architecture of the system. It's not, you know, bogged down in the details. And you can make diagrams, right? Diagrams are great. They let me just instantly kind of see what's going on. But unfortunately, I've found a lot of this kind of design doc, out-of-band documentation to be kind of too high level. If I actually want to understand what this code is doing, you know, reading an architecture description gives me like a little hint, but it really is not, I don't feel connected to the code in this sense. Okay, so the whole project that I've been experimenting with is kind of how to bring these out-of-band documentation things a little bit closer to the actual code. And so I've been, you know, rolling with the name literate tracing for this. It's not, you know, a totally new idea or something, but I think it's nice to have a name for it. And what I'm saying is, a literate trace is a document that explains how a software system works by walking the reader through concrete execution traces of the system. So this is the whole pitch here, is what does documentation look like if it's structured around concrete execution traces of the system? So let's just answer that question. So there's a link here, which I guess if people have their computers out, you're welcome to just go to that link. And what you will find is this page, where I've sort of cataloged my experiments so far. And so let's see which one we want to start with. How about we start with this frequent words HTML link here, which, let me bring back my screen mirroring on this side. Okay, great. So this is a literate trace that's walking through a program that Knuth wrote originally to demonstrate literate programming, which, you know, if people want to go about the differences later, we can chat about it. But basically how this literate trace works is that it starts off talking about what the program does. So the program takes a text file and an integer k, and then it prints the k most common words in the file. And it shows a concrete input-output of running the program. So if you have this program here where k is 2, and then you have the xyz, xa, it'll tell you what the 2 most common words in the file are. Then it goes through and does some, you know, relatively normal documentation stuff. It gives you an outline of the program. It tells you a little bit about the core data structure Knuth uses to implement this, which he calls a hash tree. And then, so after explaining some of that, we get to some more interesting parts. So here we're explaining how an insertion into the hash tree actually looks like, how it's actually done. And so you can see that in the middle of our explanation, we can actually jump into this kind of single-stepper block. Okay, and this single-stepper block is constructed from an actual running execution of the program. Okay, and at every step in the program execution, it updates this state visualization on the right here. Okay, and you know, something interesting about this program is that Knuth doesn't actually use pointers in any of this. He uses like a bunch of different arrays for all of the fields on the structs, and so each one of these nodes is actually an index rather than a pointer. I don't know. So you can walk through the trace here, and you can actually sort of see how all of these steps work, interspersed with prose. And so the key thing here is that, like, as you're reading this literate trace, you're actually seeing a concrete execution of the program. You're seeing how the program goes from the input file to the output file here. So we've made a couple of other, I've made a couple of other traces here that you may browse at your leisure. So for example, there's a few HTML ones showing, you know, how the hash map in GCC works. And, you know, one cute thing that you can see here is I've linked to where how they came up with the hash table. They did some sort of like empirical trial and error on things. In addition to this kind of HTML view, we also have a PDF output. So the original name of Trek came from tracing with tech. So Trek itself is actually just a LaTeX plugin. So let me see, for example, here's a LaTeX version of that previous trace. So you could, you know, print it out and read it on the toilet or whatever you feel like doing. And you can see in the tech here, we can actually step through piece by piece how different lines affect the visualization here. So that's the basic, I think with any luck at this point, you've got the idea of what I'm trying to do here. And just to give some, a little bit more talking about what it is, one big aspect of these literate traces are that there are system-specific visualizations, right? So the visualization of a hash table in GCC is going to be different from the visualization of a trie in Knuth's thing. It's also directly tied to the code. So in all of these literate traces, when you see some visualization, you also see where in the code that visualization came from. Another thing about doing this kind of literate tracing is that it makes it much easier for the author to skip over uninteresting aspects of the code. So for example, in the trace of the minisat sat solver that I did, I didn't want to get bogged down in explaining how the heap is implemented, right? So minisat uses a heap, or you might call it a priority queue, to organize its variables to figure out which variable to decide on next. I don't want to get bogged down in how it's implemented, but I also don't want to leave the reader guessing what something like a pop does. And so the nice thing about having this visualization is that you can actually see the effects of things that you've skipped over. So I don't show what a heap remove min, I don't tell what a heap remove min does, but you can see the effects, at least everything you need to know for this concrete execution. As we're going to see in a second, these literate traces are actually built from the code itself. So when I built that HTML page, the build system literally runs a copy of the program in GDB and extracts the state into HTML. And similar, the LaTeX interpreter is actually sending out to some GDB process and saying, what is the state right now? So it's fun, but also it's correct by construction. So as long as your visualizations are being taken from the running state of the program, you're not lying to yourself in some sense. I wanted to mention some sort of prior concepts here. You may be familiar in the education sphere with PyTutor. This is a cool single stepper for Python. And the basic thing here is we're saying that's great and students love that sort of thing to see exactly what's happening. Can we scale it up from a 10-line Python program to Git or GCC or whatnot? It seems like to some extent we actually can. And then in comparison to literate programming, so obviously that's where the namesake kind of comes from. Literate programming is actually a technique for programming. So this is something that I didn't really appreciate so much at first before reading more about it, is that Knuth really views literate programming as a way of programming. He thinks that if you write your program as a literate program, then your code itself will be better. And so literate programming is really a way of making code that doesn't exist yet better as you're writing it. And the question here that we're saying is if we accept that there's this big chunk of code that's not going to change much, how can we make that code more understandable? Okay, so just some things to think about. Let me give you a sense of how it actually works, how you make one of those traces. So this is the demo area, so we can feel free to oh man, yeah, that's horrible. Is that any better? I'm not sure I can. is the big problem here. Okay, why don't we just do this? Why don't we instead just walk through the quick start, because I think the quick start will show you all the code basically. So here's how it works. If you go home today and you want to try your hand at making one of these documents, what you do is you clone the Git repo. It's on my website here. You go in. I've already got a template example in the examples directory, and then you delete mypackage.py. You don't have to do that if you don't want to. Okay. So then you need some code to trace, right? And for this little demo here, we're just going to trace this dumb linked list program. So it just creates, you've got linked list nodes, and then you loop over and create a linked list of 4 items. So you go ahead and just in your little directory for your trace, you go in source test.c, and then you dump this program in there, and then when you run make, it'll build it. Okay, so you've just got this program, and it's built with debug symbols and everything. Okay, now you're going to write an HTML document. This is probably unlike any HTML document you've written before, okay? And the reason is because you do some random stuff here that it's not only HTML plus some LaTeX syntax, but it's also HTML plus some LaTeX syntax plus some GDB, Okay, so it's a lot of different stuff going on here. But basically, it's an HTML document, and then in random places, you can say things like, set the executable to be traced. Okay, and this is just source/test is what we built from that C file earlier. And then you can say, initialize some Trek modules, right? So the print code plugin or the GDB eval plugin, okay? Then you just continue writing your HTML document, and when you want to print out some source code, you just use print code, and it's going to use pigmentize to pretty print that code. This HL here means highlight line 11. And then you continue writing your document, and you can use, for example, the run until command. So while this HTML file is being compiled, GDB is running in the background, and you can control GDB. So you can tell GDB, run that executable until it gets to line 11. And you can say the first time line 11 is reached, write out that node is equal to, and then evaluate the symbol node. Okay? And then you can run to line 11 again, and say on the second time it's reached, it has this value. So this is really just a normal HTML document with some of these commands. Unfortunately, the screen sizing in Zoom here doesn't play well with my bad CSS abilities. But as you see, what you get out after compiling that is it has printed some of the source code. It says on the first time it's reached, node is null, which makes sense. On the second time it's reached, node is some non-null pointer. Okay. Now let's talk about how do we make some of those visualizations, right? So for this, we're going to use a custom Trek module. So we're going to initialize this module called visull, and then after running the loop a few more times, we're going to visualize we're going to call llviz node. Okay, so what is visull? Visull is just a Python file. So all Trek modules are just Python files. And this Python file gets to interact with the GDB Python API. Okay, so you can see here, this is the GDB Python API. It's parsing and evaluating whatever you pass in as the start node argument. Okay, so when we called visull, we pass node. So that tells it to evaluate the node variable in the C file. And then we can just loop through the linked list in Python. And as we loop through, we're creating sort of graph nodes using the Trek graph interface. And then we return this dictionary saying the sort of HTML view of this response is, whatever the graph's HTML code is. Okay, and then we add this Trek command decorator to tell it this is a command that should be available to Trek documents. So after we do that, we're returning the HTML code for the visualization. Ta-da, we see the linked list visualized at the end. And this visualization is correct by construction. It's extracted from the actual running instance of the code. I also showed you the single steppers. And so the single stepper thing is just another Trek built-in package. And so the syntax for using it after you import it is that you do \single stepper, you add some optional arguments. In this case, it says single step until you reach line 16. And then you tell it what lines to actually show the single stepper for. So basically in that clicker, you're going to see a frame in that clicker every time it reaches line 10 through 15. So in your single stepper, you don't actually have to show literally every line that's reached. You can sort of keep it at a certain level of abstraction. And then inside the second non-optional argument is just what is going to be displayed for every step of that single stepper. In this case, it's going to say at this line, node is blah, 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 and then the visualization of the node itself. Okay? And so then if you compile that, what you'll see, and it's a little bit of an L because it's zoomed in too much, but what you'll see is that the single stepper is stepping through, and as we go through the loop, we're going to see node actually build up the list. And so it's actually, for once you get the hang of it, it's less surprising, but this is basically how it looks. Okay. I wanted to say a little bit about describing diagrams. So describing diagrams like those graph things is much harder than you would think. I always thought there should be some super simple DSL. You just describe I want my objects are the nodes in the graph and the pointers are the edges. It should be that simple. It is absolutely not that simple. Okay, I could not get a good DSL for this, and I would beg you to try to design one if you can. So here are some things that I ran into. First of all, the edges in your graphs that you get out trying to describe the state are not always pointers. So for example, in the Vim like line tracking setup, the way that blocks are connected is by block IDs. And some of those blocks aren't even in memory, they're on disk, right? Big pain. Or in a Linux red-black tree, some of those edges are pointers to the interior of an object, not the object itself, right? And they use container of. Or they're just indices into arrays rather than actual pointers, okay? On top of that, nodes in these visualizations aren't always objects, right? In the trace of Git, those nodes may be files on disk, or they might be compressed files on disk, and you have to decompress them first before showing them to the user. Again, they might be indices, or they might even just be variables in some decision trail in Minisat, right? Pointers aren't always pointers, and types aren't always types, right? So if you have a tagged union, the system that is trying to visualize the state of the program needs some way to know which of those union options it should pick to visualize. And on top of that, you have bit packing for red-black trees. They stuff the red-black bit in the pointer. You have things that are like header structs, so you don't actually know the type even though you think you do. It's a big pain. And on top of all of that, you need a lot of control and predictability over where nodes are positioned, right? Because if you try to use GraphViz, for example, to print out your graphs, what you're going to see is that when a new node appears, all the other nodes are probably going to move around. And if you're single stepping and you're trying to track what happens to this node, you're going to get confused, right? So all of these things made this problem much, much harder than I thought it would be. And so right now I basically have no solution other than you can write Python, and I have a graph API, and you write Python that turns the GDB state into a graph. And I would really, really love to have a much better DSL for this, but I so far have been kind of unable to capture all of this annoyance in a language. The other thing you may notice here is that I have all these run until this line stuff. And so if your code base changes and the line numbers change, it gets screwed. This is kind of painful. I think two things with this. One is that apparently Git can do a very good job of tracking lines over time. So I think it should be relatively easy to have an auto fixer for this. It's also sort of a feature. So you might imagine integrating build the documentation as part of the CI. And so if the code changes, it kind of forces the user to also change the documentation. Okay, the last major thing I want to say here, this is the last slide before the summary, is just that I hope that all of you will go and try reading one of these traces, and maybe you'll get a little something out of it. But even if that is false, even if I'm the only one who ever in the world in history will ever read one of these things and it has no value for anyone else, I actually think it still has value for the writer of the literate trace. Okay, so I think the way that I like to think about it is that it gives your hands something to do while reading code, right? I want to read Vim or whatever, but I read it and am I understanding it? Am I getting anything out of it? Who knows, right? And so giving your hands something to do and saying oh, it kind of turns the process of reading code into writing code, right? Writing this trace. And it's cool at the end of the day to say, I spent a week learning about this, and now I have this, document out of it. And really, it also kind of keeps you honest, right? You might think you understand how this works. You might think you understand how this tree is encoded, but once you go to actually, extract a diagram from it, you're like, oh, I did not understand that at all. Cool. Okay, so I guess we did wait until the end for questions. I'll just say, in terms of, if you found this interesting at all, I have an increasing list of difficulty things you might imagine doing. The basic one that I just want to say is if you go to this site, you can see a bunch of traces. Maybe you're mega bored on the plane home. If you read one, and if you have thoughts of how it really didn't work, or it really did work, or how it could be made to explain things a little bit better, send me feedback. I'm a super novice writer, so any thoughts are appreciated. But yeah, happy to take questions now.
Hi, thanks. Great talk. So I have three things, actually. I'll make them quick. First one is the problems you mentioned about drawing diagrams automatically. this is kind of what my whole research direction is at the moment, so we should talk afterwards.
Yes, we should.
The second thing is, so when you say trace, the first thing I thought of before you presented what you did is kind of the extreme limit case of putting a print on every line of my code, right? And that looks a little bit different from a stepper, in that in a stepper I'm still seeing the source code as it was, but in this print trace, I am seeing a history of execution where it might be the same function calling itself, but every time it calls itself, I'm going one level deeper or something. So I'm wondering, have you thought about traces in that sense of the word too?
Yeah, so I think this notion of like, what do you do, for example, when you hit like recursion and you want some notion of call stack as well, I think is something that I haven't looked as much at. You can imagine having like a call stack on the right-hand side, for example. But yeah, we're definitely, I haven't thought much about this notion of like putting a print statement at every line, but I would love to chat more offline and hear about it.
So we have another project in our lab at the moment which is trying to build this sort of tool, which is simulate print statement at every line and what's the right interface to deal with it. The third thing I wanted to say is that, have you heard of a tool called Electron?
I don't think so.
So it's also a previous project from someone in our lab, where it's like literate tracing, but for interactive theorem provers, where often the way you read an interactive theorem prover script is by stepping through it in the prover itself, and it shows you the states on the side. But what if you don't have access to that? What if you want to have a reified object, as you said, of what the proof looks like? And so Electron is a tool that will record those outputs and make them visible as a web interface. So there might be some related ideas there too.
Yeah, I really love this, and it sounds like I should learn a lot more. Which group is it?
This is the System F lab at EPFL, led by Clément Pitt-Claudel. That's
Cool.
my PI.
Yeah, I'd love to chat more and hear about all this great work you guys are doing. I think especially if you have a way of extracting these kinds of visualizations, I think that would be super useful. In terms of this, one thing this reminds me about the printf on every line is that one place where that became a little bit helpful, because it's also sort of similar to like record and replay. And so, for example, for doing like operating system code, or where there's like a lot of timing involved, we found that like using a record and replay debugger was actually super necessary there. So maybe it intersects a little bit there.
Yeah, for sure. Yeah, let's talk after. Yeah, thank you.
Thank you.
Yeah, so I was also going to mention the Electron thing, but there's also some work that was presented, I think, yesterday at SOSP in Korea, a paper called Ghost in the Android Shell, where basically they add to a hypervisor instrumentation that in particular sort of prints the state of the thing as it goes, the logical state. I don't think they can do it purely through debug info. They need sort of extra instrumentation, but I think you should look it up.
Yeah.
But this was a comment. My question is, have you thought about sort of linking these traces with like sort of unit tests? Because in a sense, the unit test, they should sort of go through, and sort of, the assertion at the end should hold, but also they should go through in the sense of the right thing should happen, and a good unit test should also be sort of illuminating for the user. So have you thought about sort of doing like regression visualizations?
Yeah, so I think one thing that this reminds me of is definitely this concept of like putting the documentation into the CI in some sense, that like maybe some of your unit tests are actually traces, and when the relevant code changes, you have to fix your trace and kind of like keep it all up to date with the code itself. And so that might be a little bit in that direction. But yeah, I think it's an interesting idea.
Yeah, and I just final comment. Having many times done the job of taking a large piece of software and then for my colleagues, like writing this huge trace of like, okay, if we take this execution, it starts from this function, it goes there, it does this, it goes there, it goes that, then like an inline LaTeX formula, like this is great work.
I'm glad to hear it. Yeah, definitely give it a try and email me with your hate if it doesn't work for you.
Will do. Thank you.
Yeah,
Thanks, Matthew. That was really nice. Just to remind myself, to remind you, some of your problems to do with pointers into the middle of things and things like that, I have some work that might be able to help with that, so I'm going to ping you after, or if I don't ping you, ping me. But the other thing is, I feel like with documentation, there's a sort of, something a bit like the tech transfer problem, which is people do enough work to solve their immediate problem, and then there's an extra level to make it sort of digestible by other people, and that's sort of a gap that's really hard to bridge. So I don't know if you've thought about any extra layers of tooling that could, like for example, if I had a whole GDB history where I was stepping through some tricky thing, like could it like generate a first draft of a literate trace for me or something like that? Have you thought about that problem?
Yeah, so this is actually something that I would really love to have, and going the other way. So sometimes you're writing this literate trace and you're like, oh, I want to see what's going on. I just want to open like this literate trace position in GDB to interact with it. And exactly the direction you're saying of like, I've done all this to understand it, I just want to dump it into a trace to send it off to someone else or as like a first draft. And I think that's doable. I haven't done it yet, but I would love to do that, yeah.
Cool, thanks.
Hi, thanks for the talk. Have you considered reversing the control, as in now you describe which lines you want to track and you comment on them? Could you have the code, something in the code directly that says you must comment on that state?
Yeah.
And then it will be kind of, so it's automatically up to date because the code is always good. And
yeah, so I'm working on something a little bit like this, of like extracting some of these visualizations by putting things into the code. I'm not sure where I think like, you know, in terms of a sociological thing, I want to be able to write traces for other people's code as it sits, like the code in their Git repo or whatever. So doing it out of band like this is helpful for that. But I definitely think that what you're suggesting of putting things in the code itself, maybe if you have more control over the project, is the right way is a reasonable way to do it as well. Yeah. Thanks.
Okay. Are there any further questions? Then just thank the author and. By Tomer Katz, and we'll be talking about SPLASH'25.
Yeah. So, hi guys. Today I'm going to talk about program synthesis and what happened when we give it to users. So before I begin, I would like to note that there are a lot of techniques for program synthesis. And in this talk, whenever I'm going to refer program synthesis, I'm actually going to mean programming by example. In this technique, the user provides the synthesizer with a set of input-output examples, and the synthesizer will then try to find a program that satisfies all of them. One example of such tool is Loopy. It is a work from a few years ago that integrates a synthesizer into an IDE with live coding features. And as you can see here in the screenshot, this gray box near the code is called a projection box, and it actually shows the user the live values that each variable gets at this line, meaning that the IDE is continuously evaluating the code and showing the user throughout those projection boxes the live value that each variable gets. Later on, when the user would like to generate some code, he can invoke the synthesizer by typing $! Loopy will then use the projection box as an interface for the user to provide the examples. It will take the live values as input for the examples, leaving the user to only provide the output. And here you can see how the user can specify one example. But if the user would like to specify the code using more than one example, he can just add another code to the function. The projection box will be re-evaluated, and the user can now specify using more than one example. Okay, so this is Loopy, and this is how it basically works. And now I want to show you a full synthesis session and what it looks like. And for that, I'm actually going to need a task. And the task that is going to follow us today is the run length encoding compression task. This is a task from Cracking the Code interview. And as its name applies, the task is to implement a string compress function. And the compression should work like this. So imagine we have this input. We would like to replace the sequence of A with 2A, B would be replaced with 1B, and the sequence of C should be compressed into 3C. So this is the basic task. But before trying to solve this, let's focus on the heart of the task, which is going to be the concatenation. So let's try to synthesize a function that get a character and a number and concast them together. So how it should look like. The user will invoke the synthesizer and get this projection box to fill. And let's say that in the first iteration, the user will only provide one example. So he will fill the first row, press enter to send the example to the synthesizer, and the synthesizer is going to return this program. So as you can see, on the one hand, this program does satisfy the example, but it's not the general case program the user was hoping to get. So at this point, the user understands that he needs to specify in using more than one example. So we'll try again. He will delete this line, invoke the synthesizer, and it will get the same projection box to fill. And this time, he will try to give two examples. So he will start by filling the first row, and by accident, he will make a typo. So instead of 2A, he put 3A's, but he didn't notice and continued filling the second row. He filled the second row, pressed enter to send those examples to the synthesizer, and got this piece of code. Now the user is a bit confused. I mean, after sending the example to the synthesizer, the examples are no longer visible to him, so he can't really tell that he made a typo. And when he looks at the code, he sees this constant tree in the code, but he can't really recall that any of his examples contain a tree. So he's like, what's going on here? At this point, the user is, like I said, very confused and probably think to himself, okay, I'm going to give this tool another one try, or I'm going to move to ChatGPT. So he will invoke the synthesizer again, and like before, he will get an empty projection to fill. So he will need to fill the first row again, the second row again, and adding a new third example, he will fill the third row, sending those examples to the synthesizer, and finally get the program that he actually wanted. As you can see, this process of re-providing the same example that you already provided is a very tedious and error-prone process. But this is not all. I mean, what happened next? After the user got the program that he was satisfied with, he will take this piece of code and compose it together with the code that he wrote by himself, leaving no evidence that actually this line of code was synthesized and should be looked at with extra care. So to solve those problems, we propose example scopes. Basically, every solution that the synthesizer is going to provide us, we will wrap with those comments. Since the solution can contain more than one line, we actually need to mark where it starts and where it ends. And this is what gives us the scope structure that we are actually wrapping something. So as we said, we mark where it starts and where it ends. And we're also going to keep the example that the user provided in the comments themselves. And the structure of the example is quite intuitive, where the inputs are on the left and the outputs are on the right. Now I want to notice that those comments are just a normal Python comments, meaning that the user can modify them. He can delete them, edit them, and more importantly, he can also add more of them. And of course, the user can also modify the code inside of the example scopes. Therefore, we decided to add some live feedback to those comments, meaning that we are going to evaluate the comments over the code and show the user if the code that those comments wrap actually satisfy them or not. So here you can see that all of the examples are satisfied, but if the user will modify the second example, the code doesn't longer satisfy it, so we will color it in red, telling the user that it's not satisfied. At this point, and like in every other time of the program, the user can invoke the synthesizer on those example scopes, and what it's going to do is that the synthesizer is going to parse those comments, it's going to take those examples, and we'll try to find a program that satisfies those examples. So this is basically the beginning of a tool that we call Scoopy. We start by keeping those example scopes in the code, and also add some live feedback to those comments. So we can say that by allowing the user to invoke the synthesizer on those example scopes, we change the interaction model, eliminating the part where the user needs to retype the same examples all over again. Okay, so after we have the example scopes, let's go back to the original task and try to see what this extra ability that we provided user can cause. So here you can see a scratch of the solution for the compress task, where we are iterating over a string, and each iteration we are going to check if the current character that we see is equal to the last character that we saw. If so, we are going to increment a counter that counts how many times we see the same letter. And let's say that we want to synthesize the else part of this, the else part of this code. So imagine we are at this state of the program, that we see B after we saw A twice. The state is what you can see on the left, and we want that after the code in the else branch would be executed, the state to change to something like this. We would like the rs variable to contain the concatenation like we see before, so 2A. We would like to update the last variable, so it should be B. And we also want to reinitialize count to 1. So if we take this example and give it to the synthesizer, we will get this piece of code. And as you can see, like before, we have this overfitted assignment to rs. The concatenation is overfitted. At this point, we will actually try to synthesize only this assignment. So we'll delete this line, and we'll provide the synthesizer now with 2 examples to get a piece of code that seems to do the job. And it seems good. I mean, we fixed the code, but what happens if we take a broader look at our code? I mean, the first example that we provided is now colored in red, meaning that the code it wraps doesn't longer satisfy. And why is it? I mean, we fixed an overfitted code, but we actually discovered a bug. If you look closely, you can see that we actually reinitialize count before actually using it. So each time the result is going to be like 1 something, which is obviously not satisfied the example. And another thing I want you to notice is that by allowing the user to synthesize inside of an existing example scope, we actually created nesting of those scopes. So here you can see the inner example scope that is wrapped with an outer example scope. So nesting occurred. At this point, the user would likely to invoke the synthesizer on the outer example scope, hoping to get a program that satisfies this example. And what is actually going to happen is, like we said before, the synthesizer is going to pass the example in the example scopes, ignoring everything inside of it. It will take this example and will return us this piece of code, which is actually the same code that we started with the overfitted assignment. So this is not quite a good idea. At this point, we had 2 options. One option is going to limit the user and not allowing it to synthesize inside of an existing example scope, so no nested could be created and no problems. And another option was to improve the synthesizer and make it take into account those nestings. So as you may guess, this is the reason I'm standing here. We chose the second option. And like I said before, we start by keeping the example scopes in the code and add some live feedback to them. But we also propose a new synthesis algorithm that takes into account nested examples. So before I'm going to show you how it works, let's go back to the code. And just for the fun, and so I could explain more in detail later on, let's wrap the entire body of the loop with another example. So here you can see we added another example that wraps the if-else. And if you notice, we have now nesting in depth 3. We have the innermost example scope, the middle scope, and the outermost example scope that wraps all of them. So before explaining what is going to happen, I want to show you a small demo of the tool. Great. So here you can see the state that we left the slides. We have the innermost scope, the middle scope, and the outer scope. And the first thing I want to show you is that if we hover over the example, actually the tool is going to say why this example is not satisfied. It tells that rs is expected to be 2A, like it's written here, but after evaluating the code, the result is going to be 1A. I also want to show you that if we will modify the examples, it will also reevaluate and color it, and this is also true if we will modify the code itself. Plus. So the examples are now red. And the most interesting thing I want to show you is what's going to happen if we invoke the synthesizer here on the outermost example scope. So let's say the user will invoke it. And the synthesizer will think for a bit and will return us this program where all of the examples exist actually and satisfied. And if you noticed, we actually took the example that wrapped the entire else branch and brought it up to this. I'll explain later on why this actually happens, but basically we got code that fixed the order of assignments, so we are happy. So that's for the demo. Let's go back to the slides and explain what happened. So, like almost every good thing in PL, it all starts with the AST of the program. So you can see here the AST of the program that we had. And since we added the example scope to the code, we also need to represent those example scopes in the AST. And we do this by showing those green boxes. So each box wraps the code that corresponds with the code that is wrapped with the example scope. And when invoking Scoopy on those example scopes, it will start to iterate over this AST and try to find a program that satisfies those example scopes, and that the iteration of actually synthesized will take into account the example scope's location and their relation with one another. So the iteration is going to be a bottom-up iteration, meaning that we are going to start from the innermost example scope. And the algorithm goes like this, and each time we're encountering an example scope, we actually need to look at the node's parent. So if we do this, we can see that E2 is a part of sequence of assignments. And at this point, at this case, we're actually going to take a flat synthesizer. I mean, a synthesizer that can find a program that discards with only normal examples. We'll take the examples from the example scope, send them to the synthesizer, and get a program that satisfies those examples. We will keep this program aside, knowing that we need to include it later on in the solution, and continue the traversal. So we continue, and we can see we're encountering another example scope, E1. Like I said before, we need to look at the node's parents, and we can see that E1 is a son of an if-else node that is also wrapped with an example scope. In this case, we're not going to take E1 and send them to the synthesizer. We're actually going to do something more sophisticated. As you can see, E1 and E3 actually describe the same code block, you can think of it. So we actually can unite them. So we will do this before sending them. So we will unite the examples. But the union is not a normal union. We also want to remember that the example from E1 came from the same branch of the code. I mean that later on, if we have also an if-else in the solution, we would like to keep the example from E1 describing the same branch. So after the union, we will take the code that we found earlier, send this to the synthesizer, and ask the synthesizer to find a program that satisfies this example union, but also include the program that we found earlier. So the synthesizer is going to return us something like this, a program that satisfies E1 and E3, but also include the program that we have before. So this algorithm that I just showed you with the animation can be described with those inference rules. So for example, the cond rule tells us what to do whenever we encounter an if-else node. And those two scopable rules describes as what I described as looking at the node parents and decide what to do based on it. And any question of those inference rules? I guess no. So let's do a small recap of what we saw. We started by leaving example scopes in the code. We added them some light feedback. We saw that those example scopes could be nested one in each other, and we also see how we took a synthesizer and make it find a program that satisfies all of the examples. Okay. At this point, we want to see if this new ability that we gave the synthesizer actually affected the expressiveness of it, meaning that is the synthesizer is now able to find a program using less examples. So to do this, we started by collecting 50 programming tasks and started specifying each of them using nested set of examples. Later on, we took each task and we also needed to describe them using only top-level examples. So we took each nested examples and removed the nested examples, leaving us with only top-level examples for the program. And we gave those top-level examples to the synthesizer and saw if the synthesizer was able to find a solution. If it didn't able to find a solution, we added more examples, tried again, so on and so on, adding more examples until the synthesizer was able to find a solution, or we needed to add 5 examples and then we stopped because we didn't want to add more than 5 examples. So at this state, you can imagine we have 50 programming tasks that are described once with nested examples and once with top-level examples. And we wanted to calculate the difference in the total number of examples for each description. So imagine we have this scenario where a task was described in the nested form using 4 examples, and in the flat form using 3 examples. We say that the difference is -1. But if we have a program that is described with 4 examples in the nested scope, in the nested form, and with 5 examples in the flat form, we say that the difference is positive. So as you can see, the difference can also be negative and also can be positive. And of course, it can also be 0. So here we show you the number of benchmarks that the flat synthesizer was able to solve as a function of the difference that we just calculated. So like we said, we have 50 benchmarks that Scoopy was able to solve. Out of those, 40 benchmarks the flat synthesizer was able to solve, and the remaining 10 the flat failed due to a timeout or that 5 examples weren't enough, and then we actually stopped. In the negative part of the graph, you can see the benchmark that the flat synthesizer was able to solve using less examples. And in the positive part of the graph, you can see the benchmark that he was able to solve, but he required more examples. So if we sum the number up, we can see that Scoopy was able to solve more than half of the benchmarks using less examples. So we actually gained some expressiveness. So yay. After that, we wanted to check Scoopy's ability with real users. So we conducted 2 user studies. One user study was in order to test the effectiveness of example scopes and the live feedback we gave them, and another user study to test the ability to synthesize nested example scopes. So let's go to the first user study. The first user study was within subject study that had 6 participants, and the research question that we wanted to answer was, does keeping specification help understanding synthesized code? And in order to test this, we actually created 4 debugging tasks by synthesizing each line of the task. And you can see on the left the control settings, where we did not include the example scopes. And on the right, you can see the same code, but actually with example scopes. And we asked participants to find the bug and fix it. Here you can see the time it took each participant to solve each task, where the dashed line represents the average time it took for each group. And as you can see, in all of the tasks, participants who had those example scopes actually took more time to solve the task. We believe this is because they were more engaged with the examples and the code itself. One of them told us, I don't think there is any problem here, but let me just add another example, meaning they were like playing with the examples. Another thing I want to note is that each participant who started solving the task with example scopes asked them back when he moved to task without them. So it's nice to know. Moving on to the second user study, it was a between subject study that we split the participants into 2 groups. One group got Scoopy, which is its full ability to synthesize nested example scopes, and the other group got Scoopy, but when trying to invoke the synthesizer on nested example scope, the synthesizer is actually used only the top level examples, ignoring everything else, like we saw before. And I'll just say that both groups went to a guided first task, knowing the ability of the tool, meaning the first group knew that the synthesizer is going to take into account nested scopes, and the other group knew that the synthesizer is not going to take them into account. And the research question that we wanted to answer was, does the ability to synthesize nested example scopes help programmers? And help programmers in 2 scenarios. One, does it helpful with unfamiliar code? And another, is it helpful with a familiar code? And actually, to create a familiar code, we needed to add another middle task, a scaffolding task, where we ask participants to synthesize code, so we have some code that they are familiar with. So let's go to the first task, the unfamiliar task. So like before, we measure the time it took each participant to solve the task, and those are the bars you can see here. The dashed line represent the average time it took each group, and bars with hatches represent participants who did not finish the task due to a timeout. So, like you can see, the success rate of participants who had the ability to synthesize nested example scopes was higher, and the time it took them to solve the task was lower. So it's a good thing. And if we move to the scaffolding task, we actually did not expect to see any difference in the result because there was no need to resynthesize nested example scopes. And like we expected, we actually didn't see any time difference. Moving on to the familiar code task, this time we saw that participants who had the ability actually took more time to solve the task. And we believe this is because the participants were more afraid to invoke the synthesizer on those nested example scopes because they were not sure actually what is going on behind the scene in comparison to the other participants who actually knew exactly what is going to happen. And they told us this throughout the whole study. I mean, one of them told us that if I touch the outer scope, it will disrupt all the inner, and if I synthesize the outer scope, it would delete everything. I mean, it's not that they were happy with this, but they actually know that the synthesizer is only going to use the outer scopes. We also saw this in a survey that we conducted after the study. One of the questions that we asked them was, did you trust synthesized code when resynthesizing multiple nested examples? And also here, we can see that participants who actually had the ability to synthesize nested example scope trusted the code less. So to sum up, we saw Scoopy. It starts by keeping example scopes in the code, add some light feedback to them, and propose a new synthesis algorithm that synthesizes nested example scopes. Or in other words, enhancing program synthesis with nested example specifications. Thank you.
So I have time for a few questions. Please go ahead.
Nice talk. I was really curious about the conclusion of having the comments, because with prompts, they're deciding on doing exactly the same thing, having the prompt as a comment in the code. My question was actually about when you synthesize the top level and you provide the current synthesis for the lower nested example as an ingredient. The synthesizer doesn't modify that ingredient at all, right?
Yeah.
But it could be the case that you have an overfitted example, and for instance you have a constant 2 or whatever, that when you synthesize the outer block, you might want to replace it with a variable that's available outside. That would make the inner code examples work, but make the function more general. Would it be possible to modify the synthesizer to include it?
Yeah, actually I think so. I mean, the requirement to include the same code as is could also be modified. So I guess if you have some innovative ideas to actually make it use other pieces of code that we can see or new pieces of code, it's all possible.
Okay, thank you.
Thank you very much for your talk, and I think it's a very nice idea to build an explicit relationship between the examples and the synthesis code. But I'm wondering, when the set of input-output examples is becoming really large, would it be difficult to manage or understand the synthesis code even with Scoopy?
If I understand what you ask, I mean, like, if we have like big example, I mean, a lot of in the input state and a lot of in the output state.
Oh yeah, a lot of examples.
A lot of examples or
Yeah.
large examples?
Yeah.
A lot of examples?
Yeah.
I mean, I think it's going to be difficult to understand if you have actually a lot of examples, but the good thing is if we have a synthesizer that is able to solve more general code using less examples, this actually is going to be great. I mean, if you can specify the same code using less examples like we show here, I think you would need like less examples, so you don't have this example.
Okay, thank you.
Thanks for the talk, really cool stuff. Just a very tiny technical question. So if the user would refactor, for example, rename one of the variables, will that be also propagated to the comments, or? Yeah.
Okay. Yeah. Just to clarify, if you will modify the code or the examples?
Either way.
Basically, Scoopy is only going to look at the examples. I mean, he doesn't look at the code at all, as like if you can see here in the algorithm. Just a sec. You can see that the code is actually absent. I mean, look, it look only at the examples. So the most important thing is the example that you're actually going to provide. So if you modify the example, the code is going to correspond to this.
Thank you.
So are there any further questions? Should thank the speaker then, and that brings us to the end of this session.
Kevin Gruff, who apparently once came to my talk 10 years ago and remembers me, but unfortunately I didn't remember him. Unlike when I gave that talk, when I must admit I was pleased there was an AV problem because that gave me enough time to finish my slides. Kevin assures us that his slides are done. He's an independent researcher, kind of working as, I think, an itinerant tech writer, more or less. He will write words for food. I don't know if he actually wants to do a PhD, but if you know, he is an independent researcher, which is quite an interesting thing in this day and age. And he's here to talk about multiple writing systems, how you can support, I guess, different scripts and different systems. We all know in Unicode, we all know that it's not really the solution we all hope it would be, but maybe Kevin has some ideas, and since he's outside the US, he is able to prevent work, you know, which relies on the assumption that the Queen's English was not actually good enough for Jesus Christ. Kevin.
All right, thank you. The mic is right? Okay, is it good? Okay, perfect. Let me plug this in. All right. Wait for that to show up. Give it a second. Okay. All right, so my talk is called Carving Text at Its Joints, a New Perspective on Writing and Computers. So let's just jump right in. So this is kind of an outline of the talk, but I'll just skip over this because we'll see it again. So introduction. So everything is human-made in this, I just want to clarify. So to begin with, computer users rightfully expect to be able to input, view, transform, and edit text in their own language, in their own writing system, and you know, it's 2025, so software must reflect that fact. English only, ASCII only, fixed with fonts, they're just not going to cut it anymore. So, what's the problem with that? Writing is hard. Human writing is quite difficult. We have come quite a long way over the past 3 decades, but much work remains. The modern tech stack, it can almost get us there, but there are major open problems, by my estimation anyway. So, the thing is, this extreme complexity really economically disincentivizes minority or minoritized writing system support, because those often work out to be, you know, the most complicated, not the least of reason because there's just less experience with them, less of corpora and so forth. And that can further contribute to their marginalization. You know, if you can't text, you can't email in your writing system, in this day and age, it is in a quite marginal position. So I think as a matter of linguistic justice, there is a particular urgency, I think, to the subject that I want to talk about today. So what is my goal here? I've kind of ripped off Milton. My goal is to justify the ways of linguist to computer scientist with his own characteristic humility. So I want to argue that the way that we've treated text heretofore is wrong. And to understand why, we need to historicize the basis of how the status quo came to be. I think that the apparent complexity is largely extrinsic, not entirely, but largely. And it's really the result of bad or, in many cases, no abstractions. What happens is that the particulars of every writing system sort of intrude into every application because there is no abstraction. And the correctness kind of appears locked in this internal struggle. But I come bearing and offering a piece. Tractable and correct text handling is possible if we are willing to radically rethink what computer text is. So let's do that. And my quote is or my title is a reference to the Phaedrus, Platonic dialogue that deals with the origin of writing. Of course, in it, Socrates says that writing is the worst invention in history, so maybe it's a bad reference. But I think what we need is a proper philosophical account of what computer text is, which is a term that I've been quite insistent on. So I have 2 solutions. One is an alternative style of text encoding, and another is a model of programmable digital typography, or computer typography, and I'll get to that, both of those in due time. So I'm guided here by kind of 3 aphorisms. There's no such thing as plain text, fonts are programs or functions, and writing is an interface, writing systems are its implementations. So, next section. Here's just some definitions that might be helpful. So a grapheme, that's a tendentious category in graphematics, which is kind of a weird field. But basically, it's kind of the smallest semantically meaningful unit of writing or text. A logogram is a symbol which denotes a word or root instead of a sound or syllable. A quadrat, this is a Mayanist and Egyptological term, but you'll see what it means in a second, but just bear the word in mind. And a diacritic, I'm sure many of you know this word, but it's just something that modifies kind of a base glyph. All right, so I'm really interested in the Maya script in particular. So I want to introduce this briefly just so we have a common ground. It was developed in about the 3rd century BC. It is one of only 4 independent inventions of writing that we know of, the other 3 being cuneiform, Egyptian, and Chinese. That is, linguists disagree about this, but those 4 are unambiguously known to be independent, more or less. And it was used to write the classical Maya language. It was suppressed by the Spanish colonial authorities in the 16th century, and then thereafter forgotten. Now, I put this slide up just because I wanted to show you a picture. I think this is one of the most amazing portraits of all time. So this guy, it was a Soviet linguist, Yuri Konorizov. He was the one who deciphered the Maya script in the mid-20th century, but it is still not fully understood, and we will see that in a second. So here's just some more examples of Maya. The Maya script is this part right here and right here. The rest are more illustrations of what's happening in the text. This is another Maya text. This is printed. This is in one of 4 known Maya codices. This is the so-called Dresden Codex. Now, why care about a dead writing system? It's an interest of mine, but why should you care? Well, I have 4 reasons. So there is periodic interest in reviving the script for contemporary Mayan languages, which have millions of speakers. Maya is complex. It is highly complex, and it's a good stress test for software. By the same token, it's very different, and it challenges faulty assumptions we have about text. But also, I think it's just inherently interesting. So let's actually look concretely at some Maya text. So this is a glyph, it is a collection of glyphs. It says he or she, there's not gendered pronouns, sat. But there's more here that meets the eye. So Maya text is organized into blocks called quadrats. I used that term before. But note that what you are seeing on the screen is not a grapheme. So, guess in your head about how many components you think this has. And I'm going to spoil the answer here in a second. The answer is 4. So I've color-coded the different ones. So let's look at what that means. So I put a transliteration up there, or I really should call that transcription, because it's giving an account of what these individual glyphs are. But you'll notice in the pronunciation, it's not chumulaha, and note that the J is pronounced like it's in Spanish. It's something like chumlah. Written Maya has a quite complex relationship with its actual vocalization. Some glyphs functions as logograms, such as chum, which is like a logogram for sit. Mu, this little blue character, is a phonetic complement. So it's not directly pronounced. It kind of gives a hint to pronunciation. It's giving a hint that the chum ends in a bilabial nasal sound, an M. But Maya is actually mostly syllabic, and this was Konorizov's great insight. If you're interested in the decipherment of Maya, I can tell you a little bit more about it after the talk. But Maya can't easily represent closed syllables, so its solution is to sort of fake it. You write 2 syllables that have the same vowel, and you ignore the second one. And that workaround is quite common cross-linguistically. We see something somewhat similar in Linear B, which was used to write Mycenaean Greek. Maya is ridiculously complex, as you can see here. This mu character, this phonetic complement, is infixed. So there is a full-size version of that glyph, but here it's being superimposed, shrunk and superimposed over the thing that it's modifying. Maya quadrats that I have seen can have as many as 6 independent components, and these aren't diacritics, but those exist too. At least I'm aware of one diacritic in the Maya script. Quadrats also frequently include numbers, and we'll see examples of that. So this next section I want to call 3 myths that computer scientists believe about text. The thing what I want to say is that computer text, it really is its own modality of writing. It's a unique phenomenon. And the reason why that is because it just has modalities, modes of use, modes of interaction that don't have any analog in other forms of writing. Like you don't backspace on a well, you kind of can on a typewriter, but you don't have arbitrary insertions and manipulations like on a typewriter. So there are questions that have to be answered. So how should backspace work? Should the cursor, in the case of Maya, travel inside a quadrant? It seems like it should, because if it couldn't, imagine if you could only delete English at the granularity of a word. That would be very annoying. But there's no obvious answers here. We really are living in a Latin world. Maya also just had, we can't ask a Mayan how it should work, or an ancient Mayan, I should say, because the system is dormant, and it also had no print tradition. So the bottom line, there may be no single fact of the matter about how these interactions should work. And there's more familiar examples like, backspace. Does that delete a whole letter or part of a letter? In languages that have very complex stacking diacritics, it might be quite annoying for the same reason as Maya. Myth number 2, there are no new writing systems. So here's just some counterexamples. These are all writing systems that developed past 150 years, starting with Cherokee, which some of you may be aware of who are American, and ending with this last one I'd like to talk a little bit about, just briefly, that a colleague of mine and friend introduced me to about a year ago exactly. This is an emerging writing system that's kind of designed to give a common orthography to many related languages in southern Africa called Ditema Dinoko. There's another name for it that is quite hard to pronounce for me, so I will not attempt it. Last myth, writing is a linear sequence of symbols. And so I won't read it for you, but I find this quote from Yannis Haralambous and Martin Durst quite helpful as an example, or as a characterization of this phenomenon. So let's look at some examples. Nastaliq is a variant of Arabic, and I just want to point out, it is difficult. This is not how it's normally written. So it's not normally written in this pinwheel shape. These are, individual lines right here. But the main conceit is that words are written kind of at a diagonal, and they sort of overlap diagonally. But what's crucial here is that from a Western typographical perspective, there are as many ligatures as there are words in the Urdu language or whatever language it is being written in. This is a poem by the Persian poet Omar Khayyam that you see. Bidirectional text, everybody knows about Hebrew and Arabic, no surprise there. Though I will note, for people who don't speak either of those languages, myself included, European Arabic numerals, it's kind of a funny thing, they were kind of borrowed back into the modern Arabic script. They are written left to right still. So pretty much all long Hebrew Arabic text which uses Western numerals is bidirectional, as is embedded Latin text is of course written left to right too. Now let's talk about vertical text. What you see on the screen is a bilingual sign in Chinese and Manchu from the Forbidden City in Beijing. And you will notice the Chinese, it is written vertically, but the glyphs are not rotated. They're written in the same way they would be written if they were written horizontally. Manchu, on the other hand, is basically a 45 degree, 90 degree rotated Syriac, basically. That is his ultimate origin, although it's diverged quite a lot. And vertical writing really doesn't refer to one phenomenon. As I talk about here, you can be written in columns left to right, right to left, and so forth. And how does horizontal text interact? So the traditional Mongolian alphabet is written only vertically. The Mongolian government plans to reintroduce the script. Software is really not ready, so I think this just kind of highlights the urgency of vertical script handling. So, all right, we've seemed like we have left to right, right to left, top to bottom. Surely no one has written bottom to top, but you would be mistaken if you thought that. The Ogham script, Ogham, was used to write a early form of the Irish language, and it is written bottom to top, typically, in epigraphic in epigraphy. So here's another example. This is a script probably haven't seen before unless you're into this kind of stuff. These are Anatolian hieroglyphs. They're used typically to write Luwian or Luwian. It's typically written in a boustrophodon order, so that is to say alternating lines of left to right, right to left. and the human and animal-shaped glyphs face the start of the line. However, within a line, glyphs may vertically stack. So, it's quite complex. All right, so how is Maya text read? Horizontally or vertically? And the answer is yes. It is in both. It is typically, though not always, written in a zigzag pattern, and then, if there's an odd number of columns, the last is vertically. And consider that the quadrant also has an internal reading order. Egyptian, everybody knows Egyptian. It is quite, well, I mean, you've seen it before, I mean to say. Left to right, right to left, just like Luvian, or Anatolian rather. It is also organized into hieroglyphs. And I will note something interesting about Egyptology is that Egyptian typography is quite common, or typesetting, I should say, is quite commonplace. That's quite routine, because hieratic, and I'm going to make some Egyptologists groan by saying this, but it's a kind of cursive hieroglyphs, so they're often transcribed into the normal ones. And this cartouche right here is a name you probably recognize. It is Cleopatra, although not the famous one, I think. I think this is Cleopatra II. The famous one is the 7th. And then I'll just mention here briefly math, music notation. These kind of get at the boundaries of what text is. Do these count as text? I'm not sure, but I think they're just worth mentioning. So in summary, even writing direction is far more complex than we might imagine. Seemingly every possibility has been instantiated somewhere, and when we consider multi-directional text, the space just explodes. I think what's important is that complex scripts seem to have a global and local writing direction. It almost has this sort of fractal character to it. And the physical order, especially in Maya and Egyptian and Anatolian, really just doesn't neatly correspond to the kind of logical reading order. So, we're going to talk about Unicode now. So Unicode, it's had some major success. It really is universal. I gave a version of this spiel to someone at a previous conference. They said, okay, yeah, but I remember the pre-Unicode days. So, it might be hubristic to criticize it, but I don't think any technology should be sacrosanct. So I want to offer some critiques of Unicode, but I'm going to duck for any flying tomatoes. So, Unicode is about plain text. Formatting explicitly outside of its purview. And what do we mean by that? Well, what does the Unicode specification say? It says, plain text is the underlying content stream to which formatting can be applied. It must contain enough information to permit the text to be rendered legibly and nothing more. And I want to deconstruct this category. So, computers, I think, really have a dual ancestry. There's this kind of highbrow, stuff of Frege, Peirce, Gödel, Turing, Church, von Neumann, Ada Lovelace. But there's also the more banal, the typewriters, teletypes, Baldo codes. And that latter category is really where we inherit the kind of typographical restrictions that I, anyway, associate with computers. So I want to share a sort of fable with you, and this is a story from the history of English. So this is a Middle English poem from the 14th century. It's called Piers Plowman, or The Vision of Piers Plowman by the poet William Langland. And I want you to look closely at this Middle English text, and I have a modern English translation for you here. So see if you notice anything. And what you'll notice is that there's this strange character here that I've highlighted in red. Now, this is a letter called Thorn. It is adapted from the runic alphabet, which I'll show you an example of in just a moment. And it denotes the dental fricatives, the TH sounds. We're going to ignore eth for a second. You can ask me about it afterwards. It's still used, the thorn is still used in modern Icelandic. So this is the most famous example of Anglo-Saxon runes. We're looking at Old English, not Middle English, and you'll note this is not the Latin alphabet. And you notice there are thorns right here at the bottom that I've highlighted. Now, notice also that they are written right to left, as was common in the runic alphabet. So thorn clearly isn't used to write English anymore. It seems quite useful. It can disambiguate ambiguities in our orthography. So what happened? Well, the answer is the printing press. Western printing began in continental Europe. Continental European languages do not use thorn. Thus, type imported did not either. So thorn fell out of use due to technological limitations. And by the way, when you see ye old shop or whatever, that Y is short for thorn. It's not pronounced ye, it's the old shop. But it's also not that because it's fake. But anyway. So I want to talk about Nastaliq for a moment, and I have this quote from a Urdu-speaking technologist named Zirak Ahmed, and he said, all Urdu software is broken because the underlying data is broken. Now, Nastaliq really, really needs fine-grained layout control to be displayed correctly. Unicode shunts this into formatting, but the problem is Nastaliq is just kind of broken. And the thing is, it's not just about aesthetics, it's about correctness. So I also want to briefly just touch on the Han unification here. I don't really want to hold court on the subject. It's outside of my wheelhouse, but I'll just say I think the lack of formatting is a major problem. This is a problem that could have been solved that just isn't, even with unification. So let's look at something a little closer to home. We're computer scientists, not linguists. So this is Algol 60. This is a screenshot from the original Algol 60 report, and I want you to notice the syntax here. So the bolding, that is not syntax highlighting. That is part of the syntax itself. Algol relied on that bolding to distinguish keywords from identifiers. And the thing I think that's interesting is that its creators, they made it for print. They weren't constrained by what computers can do. I'll just briefly mention APL. Similar sort of thing happened in the 1990s when Kenneth Iverson and Roger Hui came to design the J language. They dumped the APL character set for ASCII, which in my opinion is quite a bit of a downgrade. So there's a lesson here. For 15th century printers, Thor was not plain text. You can read English without it, as we clearly can today. But by contrast, for the Algol 60 committee, bolding kind of was plain text. Algol 60 doesn't work without it. So many things that Unicode deem formatting are needed for correct display. And I think the consequence is that plain text, it's indexed to a time and place. It is not a trans-historical category. So next thing about Unicode, I'll talk about legacy encodings. I'm just going to mention this briefly. Many of these legacy encodings are so utterly irrelevant to the present day now, but we are paying the cost for them and will pay for the cost of them in perpetuity just by structure of Unicode because it's what causes the multiple normal forms. The last thing I want to talk about is what I call the necessity of structure. So Unicode is kind of nominally flat and unstructured, but that's not actually true. Okay, 10 minutes? Okay. So simpler, yes, but simpler for whom? Can we cut this Gordian knot and simply accept structure? So here's an example of emojis, but emojis are quite structured. Here's an Egyptian of layout control, which requires actually a context-free grammar to parse. So, okay, Egyptian or emoji are both structured, but in very different ways. Can't we just solve this problem once? And I won't go into the XML stuff, but I want to talk about now my solution to this. So I want to sketch a new kind of encoding, and it's a scheme I call telecode. If we were to do Unicode over again, how would we? It's very difficult to separate these different spheres of interest, can't always be neatly separated. Everybody wants something different, so let's just kind of do everything. So this data structure is a sequence of ordered labeled n-ary trees where you have base characters, tags, and attributes. Tags introduce and delimit tree nodes, or branch nodes, I should say, and base characters would be leaf nodes, and attributes modify both of those. So this is kind of an example of how you might encode this cartouche, where you can see the red arrow shows the order, like the byte level order of the code words. So you start with an open cartouche, open stack, those hieroglyphs, end, vertical attribute, and so forth. So crucially, telecode is a fully decomposed representation of text. Everything, including diacritics, including case, is accomplished through attributes. It is easily segmentable because each grapheme, the number of graphemes is just the number of base characters, basically. And I mean grapheme in the less tendentious computer scientist sense, something like a unit of interactivity. It is self-documenting because the properties of a character can be derived from the encoding directly because these different categories are encoded in different encoding spaces. I want to briefly talk about my self-normalizing scheme, and then I'm going to move on to the typography. Unicode, so let's see. One thing that's really difficult about normalization is order of attributes. Because, so like the circumflex and the ogonek, it doesn't matter which order you encode the diacritic because they're orthogonal. But with an acute accent, if they're stacking, it does matter because that has typographical implications. So the solution I came up with is that you encode the class, the kind of set, as a offset in a sequence of attributes such that it is impossible to store an unordered sequence. So I'm going to skip this page actually, and I'm going to skip that page because I want to talk about fonts as programs. OpenType, how am I doing on time? Okay, OpenType, standard outline-based font technology. Letter forms, they're just stored as outlines. Here's an example on the right. Uses the shaping models, but they're sometimes inadequate. It tries to sort of, it tries to account for all complex behavior languages ahead of time. Difficult parts of text rendering, hinting, which is basically fixing up outlines at low resolutions. Kerning, I think many of you know what kerning is, but I have an example. Shaping, I have an example of poorly shaped and well-shaped at the bottom here. So my claim, fonts are functions from abstract text to concrete visual forms. If we do this right, then all these modes of use can kind of fall out from a much more general mechanism. And for systems that have this sort of unbounded number of letter forms, I really don't see another option. I'm going to skip this so I can get to the other thing. I'm sure many of you know about Metafont. I'll just say briefly that Metafont, it doesn't have the generality that I'm looking for here. So let's talk about my approach to this problem. It is a typography engine I've called Dubsar after a Sumerian word, and you will see those cuneiform characters typeset with the software at the top. It is merely a program in the language of the bytecode, and the code is constructed such that it kind of presents a uniform interface to all writing systems. I'm going to go over this briefly. This is quite vague because this system is in daily flux, but the basic idea is that the runtime traverses the set of trees or the sequence of trees in a depth first order, and when it encounters something I call a scribeam, something that is kind of a unit of drawing, it dispatches to a handler, which is written in this bytecode. And the bytecode can sort of arbitrarily inspect the graphic state, the cursor, it can set the cursor state, we'll talk about that in a second. It can arbitrarily inspect the input text, it can look ahead, it can look forward in some cases, and it's a stack-based machine, purely stack-based, unlike the JVM or WASM, and is statically type-safe. So it's mostly designed for telecode, this system that I've described, but you could make a font that ingested Unicode. It is stroke-based rather than outline-based. Glyphs, like Metafont, are the envelope of a virtual nib stroked along a path that can be controlled programmatically. This format turns out to be massively more compact. I have seen some quite compelling numbers in this regard, especially for large character sets like CJK. And it's arguably more semantic. Hinting, in particular, is largely obviated by the need for stroke-based because you just sort of know where the line is. You're not sort of reconstructing it. But even so, rendering PPI is a runtime parameter. It can be inspected by the code. When glyphs are drawn in the graphic state, they are tagged, and handlers can sort of inspect and modify the graphical render state at any time, up to like deleting, adding any of these individual elements, and they can tell which component was drawn for which element in the input stream. And this actually turns out to be sufficient to implement kerning, shaping, text substitution, and so forth. Also, each scribeam handler is responsible for returning the state of the next cursor, and it can kind of turn, shrink, curve to sort of fit these complex script layout. I do block level rendering. This is a little bit controversial. But the reason why I do this is because justification is actually kind of specific to a writing system. In particular, the Arabic Kashida system, where letters and not white space are stretched. And it turns out this is actually not that wasteful. The Knuth-Plass algorithm, which is what's used in tech, compiles to about 7 kilobytes, and I suspect that that is much larger than it needs to be. It could probably be half that, I believe. But even if not, it's made up elsewhere. Here's a case study on Latin. This is an adaptation of Hershey fonts. These are early stroke-based fonts. I'm still a journeyman font designer myself. But important thing to note, there is no manual kerning. So each of the subroutine or the handler for each of these glyphs, when it is written, it's looking into its context and placing itself. So you can see right here, we have this a little bit over-kerned, I might say, E, and this T is a little bit under-kerned. But there's no kerning tables. And this, for large character sets, this is hugely beneficial because there's a combinatorial blow-up. Just, you think about every pair of letters, right? And then finally, we'll talk about Maya, my favorite subject, of course. This is a very, very work-in-progress font, but you can see here, this is a typographic rendering of that lintel that I showed you at the very beginning. And I've included transcriptions, transliterations, translations. These are not my own. They're taken from a very helpful website, mesoweb.com, very good for Mesoamerican resources. And you can see here the extent to which the Maya script is really not fully understood because there are words that are just left untransliterated. Also, I don't know if there's by any chance anybody who speaks Georgian, but this sound is the same as the k in Georgian, just side note. Anyway, this took a lot of work. I'll just say that. This is a long bit of work, and it's still very much a work in progress. So, onward. Because we are onward. Where does this leave us? Can Unicode really be displaced? Are font designers going to become programmers? Well, look, I'm not delusional about this anyway. I don't think that I'm going to replace Unicode, but I do think that thinking about text encoding can maybe inform better text data structures in programming languages, operating systems. My strongest claim would be that I think that operating on Unicode directly is pretty much always mistaken, I think. I think, as an interchange format, so be it. But there are applications where interoperability doesn't really matter, like embedded programming, and maybe a different encoding would be perfectly fine in that circumstance. Lots of old video games didn't use ASCII, for example. They would use their own encoding set because nobody's going to read it. It doesn't matter. But I'm forging ahead with it in my own work, in operating system and PL stuff that I have hobby projects or whatever. But I'm much more sanguine on programmable typography. I do think that this is something that can work. I am working on a public release of this software system, and the last slide will have a link to that if you want to take a picture of it. I think this is possible, and I think this is borne out by recent developments in the Harfbuzz, Shaper, and so forth. So I think there is an appetite for that. So with that, I will leave you with this other quote from the Phaedrus and questions, if there are any.
Excellent, that's perfectly timed, and we do have time for questions. Would people please use the microphone so they can be recorded and transmitted?
Hi.
Hello.
So, yeah, I guess I have two questions.
Please.
My first one is about, let me know if you've already addressed this. So in Chinese especially, there tends to be recursion in characters because you have you only have a set of 8 or so basic strokes and they compose.
Right.
And then these compose, so does this system, does this handle this well?
Yes, it definitely could. I will say really don't know much about Chinese. I actually need someone. I need to work with someone who does, because okay. Well, there you go. I'm very ignorant about it. So if you want to, please, any Chinese speakers, please contact me. So very helpful.
My second thing, I guess, is it's not so much a question. I'm very, very excited to see another historical linguistics interested guy.
Oh, well, thank you.
And
thank
so,
you.
I'm wondering if you've ever thought of, apart from typography, if you've thought of applying historical linguistics to how programming paradigms evolve and that sort of thing, idioms and conventions.
That's a really good question, and kind of. I won't. Maybe I'll talk to you after that. But it's a very good question, and yes, I'll say yes.
All right. We should talk.
Yes, let's talk afterwards.
Hi there, really cool work, as
Thank you.
Everybody's going to say. So something you didn't touch much on about when you're talking about plain text, but I was reminded of when you talked about case, is the presence of localization and plain text and how those interact. For instance, what is uppercase dotted I? It depends on if you're speaking Turkish.
Yes, exactly.
What is, and also word ending things. You talked about normalization and in Arabic and Greek, in Hebrew and you have word-ending forms, which are those normalization? What is a word ending? So, you already wanted to complicate the notion of plain text, which is great. Do you see, this is sort of ill-formed, but how do you see localization and language dependence playing into these normalization notions?
I'll just say the Turkish eye problem has vexed me, because it's
You and everyone else.
Many people in the paper. I didn't talk about this in this talk. It's kind of morbid. I feel bad about laughing about this, but there's actually a case where mishandling that led to someone being murdered.
I recently shared this article with someone.
Yes. So it is actually quite significant. I don't have a good answer for that. This is a very vexing question to me, I'll just say. And inchoately, I would say some kind of metadata tagging has to be the answer here, basically.
All right, cool. Thank you.
You're welcome.
Hey, Kevin, really cool talk.
Thank you.
I have a more programming question. So,
Please.
So Unicode, of course, has all sorts of problems with, say, indexing. They're not all constant width, and lots of people would like to believe that an array of characters is literally just something you could jump into the middle of. So anyway, so now I'm thinking about telecode. Okay, so can you tell me a little about programming with telecode, and what actually is the data structure that I interact with if I'm writing a program that's manipulating telecode?
Yeah. So I just for time's sake, I skipped over the slide where I talked about this, but two things. The data model is quite similar to XML. So you're talking about regular trees. That's what telecode is basically. It is, like I said, quite similar to XML. For indexing into Grapheme is similar in complexity to indexing UTF-8 by code point, if that makes sense. And that was an intentional design choice, because a Grapheme is always started by a base character, always.
So there is a way of jumping to the beginning of something.
Yes, you can jump to the beginning. The encoding that I'm working with is self-synchronizing, and the way UTF-8 is UTF-8 OID. The other thing I'll say is that I envision for this, the analog of regular expressions would be like regular tree languages, basically. So like XML schemata, very similar. And I didn't have a chance to talk about it, but they have a lot of this, as I'm sure you know, similar closure decidability properties. So it actually works out to be a quite nice analog. And this came out of experience with XML stuff, so.
Yeah, good.
You're welcome.
Yeah.
Hi, thanks. First, I would like to just mention, if you're not familiar, Ramzi Nasser's Arabic programming language.
I do know about this, yes.
And really the question, my question though is about, with Dubsar, how does it deal with more graphic properties? Are there things like stroke width or virtual, stylus, medium, that sort of thing?
Great question. So pins, which I borrowed heavily from the Metafont model, you can change the width, you can change the orientation, you can change the shape of the nib, so it's like an ellipse. It can be an ellipse that's changed in orientation. It can change dynamically, which Metafont actually can't do. So that's basically the idea here. Yeah. So, thank you.
I'd like to clarify, I have no experience myself with Han characters as a person who writes them, but maybe if you have eyes and you look at Chinese text on a screen, you'll see that sometimes the fonts don't match because the people who design the fonts don't have full coverage. Do you see this as sort of a fundamental issue with Unicode that your thing would fix, or do you think this is sort of more of a font designers need to think really hard? Also welcome for people who do speak or write with languages that use Han characters to talk.
Sorry, so the question was, you're saying like font selection?
So like people who design fonts using Han characters often don't cover the full set of Han characters. So when you render them, it doesn't match visually.
I'll just say briefly, I'm very interested in generating Han characters from like Chinese, like ideograph description sequences. Okay. I just don't know enough about it to really intelligently comment.
That's okay, thank you.
But thank you. All right.
Hello, I'm curious, so suppose that your system is developed to technical completion.
Sure.
And the only thing that's left is for people to use it or adopt it. What costs do I pay as a programmer if I want to use your system? Presumably you would have to have some, in source code I type some strings, and all of my existing tools will save that as UTF-8, so presumably there has to be a translation from source code to use your system, and then what else do I suffer in order to get the benefits? I'm curious about that.
I'll just say briefly, and I can tell you more afterwards, I would like to adapt kind of word processor, a kind of forgotten word processor paradigm for editing. It's very vague, but just in the interest of time, but talk to me afterwards, I can answer it more firmly.
Sure.
Let's all thank Kevin once again. You're here today, you're here tomorrow? Are you around tomorrow?
What?
Are you around here tomorrow?
I'll be here tomorrow.
And Kevin will also be here tomorrow. I now give to my great pleasure to introduce Jeremy from Glasgow. We are actually under instructions to start on time for the vast hordes of people who are watching online, or for the AI bot, which is going to chop up the recording into various parts. Jeremy? Jeremy, but anyway, he's from Glasgow, but he does speak standard English. Sorry. And here's something you probably don't know, a random fact about Scotland. I do have Scottish heritage myself. If you get to the website of the Scottish Parliament, you'll see that actually lists 3 languages. Not 2, 3. They list Scottish Standard English, and that's Scottish Standard English. They list the Gaelic. And there's another language which is Ullans. No, it's not. It's Lowlands, or Lowland Scots, because the Highland Scots speak Gaelic, but the Lowland Scots speak something which is not Scottish Standard English. But it's, yeah. If you want to read it, go to the Scottish Parliament website. That's quite an esoteric language, which is the link. Did you see that coming? Which is actually the link.
Thank you. On the screen is the source code. This program isn't syntax highlighted, but I can show you it's there, look. The lexemes for this programming language, the programming language is white space, and the lexemes are 3 characters which are effectively invisible. We have tabs and spaces and new line characters. And these lexemes can be grouped together to form effectively opcodes in a stack-based programming language. White space was invented, amongst others, by Edwin Brady, who went on to develop Idris, the well-known programming language. This is a program. It's in the style of the artist Pete Mondrian, but this language can't be called Mondrian because that's a serious programming language. So this programming language is called Pete. And in this programming language, you have a, well, it's not a program counter, it's a direction pointer. The direction pointer starts at the top left and is pointing horizontally right. And the direction pointer moves, and every time it traverses a color boundary, it subtracts those 2 colors and looks up that value in a lookup table of opcodes to again give you a stack-based instruction. And these instructions can change the direction pointer so it can move 90 degrees in any direction, and also to compute values on this stack. It's a beautiful program, don't you think? Thank you. This is Hello World, actually. Here is another program, this time written in the Shakespeare programming language. Here, variables are characters in our Shakespearean play. Well, actually, a character is a stack of values, but we'll just have single element values here. And control flow goes through the acts and the scenes, and you can repeat scenes and so on. And values are, well, +1 is a complementary noun. -1 is a derogatory noun. And then you multiply nouns by prefixing them with adjectives. I shall demonstrate with my Shakespeare REPL here. So here's Romeo and Juliet. And for instance, Romeo might say to Juliet, "Thou art a rose." And this will assign the value 1 to Juliet. But if Romeo were to have said, "Thou art a red rose," that would actually be 1 times 2 times 2, which gives Juliet the value 4. And you can do computational things. Thou art the cube of a red rose. Juliet is now 64. And then Juliet will reply to Romeo. Now, you see why it's a dialogue between two people, because you only say thou art, you see, so that's the assignment, so you have to know who you're talking to. So only two variables are in scope at once here in this dialogue. Juliet's going to say, "Thou art the sum of myself," she's 64, and I'm going to have another positive noun here, a plum, right? Romeo's set to 65. Now, watch this, watch this. Juliet now says to Romeo, "Speak thy mind." And Juliet is going to output, oh, sorry, come back. Juliet is going to output character A, which is 65 as an ASCII value, but never mind. If Juliet had instead said, now let me get this right, I think if Juliet had said, "Open thy heart," then instead the numerical value would have been printed. So you see here that this language looks like the language of Shakespeare, Elizabethan English, and looks like a dramatic passage, but actually, really, it's just manipulating computation in a way with which we are very familiar. Do you know, Shakespeare was one of 50 languages featured in Dick Gabriel's and Guy Steele's 50 in 50 Programming Languages Review a few years ago, which some of you may have seen. So they certainly took it seriously. And that is what I want to plead for us to do today. Let's take esoteric programming language seriously. You have been laughing at White Space and Pete and Shakespeare, but I don't want you to laugh. I want you to take these things seriously, or at least think about how they might have serious implications for us as programmers and for our understanding of what programs are and what programming entails. Here's Alan Perlis, and you may have seen his beautiful collection of epigrams. And one of his most famous epigrams is this: "A language that doesn't affect the way you think about programming is not worth knowing." Somehow, a programming language shapes us and influences our thinking. Really, Perlis has specialized to the domain of programming, the more general Sapir-Whorf hypothesis, which may have been debunked in general linguistics, but let's just go with it for now. The structure of a language determines a native speaker's perception and categorization of experience. How you talk somehow determines, or at least influences, how you think. And we're going to contend that that's true for programming languages today. So this paper is available on arXiv, and this essay is also available in the proceedings. And I would encourage you, if you haven't done so, please to read it and have a think about it. Oh, here's my copy here. Good. Right. I think, here's an interesting observation. Esoteric programming languages are surprisingly popular in computer science. So I've done a few versions of this talk, and one of the things I did at the start of previous iterations of this talk is say, put your hands up if you've written a program in one of these weird programming languages. Do it, please. Good, okay. And as in previous talks, at least half the audience puts their hand up. That's very interesting. Okay, right. Try this one. Put your hand up if you have written a programming language interpreter or compiler for an esoteric programming language. Oh, excellent. Excellent, excellent, good, okay. And put up your hand if you have invented your own esoteric programming language. Oh, well done. That's a larger proportion than in any of my previous talks, so I am amongst friends. Good, excellent. Now, here's a thing. Somehow, computer scientists harbour a sense of shame. They're slightly embarrassed to admit in polite company that they have developed esoteric programs or indeed esoteric programming languages. And I want us to dispel that sense of shame today. I want us to be proud about our esoteric language knowledge and ability. Right, just some definitions at this introductory stage. What does esoteric mean? That's the first thing to think about. And we could consult the Oxford English Dictionary and see that somehow it's to do with philosophy and it's relating to an inner circle of initiates, people who are advanced in some school of knowledge or understanding, disciples of some strange teaching that is secretive and mysterious. This is esotericism. What is a programming language? We are in more familiar territory here. So I'm going to claim a programming language as a systemized notation for precise expression of intended computational behavior. This is what the ACM Encyclopedia says about programming languages. They're both tools for directing the operation of a computer and tools for organizing and expressing solutions to problems. So I suppose one might be for algorithmic intent and the other might be for computational execution. A programming language here. So if we put these things together, what is an esoteric programming language? And this is the definition from the, I suppose, homepage for many esoteric languages, esolangs.org. It says, an esoteric programming language is a programming language designed to experiment with weird ideas, to be hard to program in, or as a joke, rather than for practical use. The bold-facing is mine. So another quick audience poll. Right. So for this one, you vote interactively. 0, stick your hand up with no fingers. 1, 2, 3, 4, or 5. So, what do you think, dear audience? Esoteric languages are a significant research area that should be investigated. So, stick your hand up with as many fingers as you think appropriate. Ooh, this is interesting. Good, good. And you can abstain by not sticking your hand up. Oh, really? Dear program chair, stick your hand up, please. But there we are. Thank you. Well done. Good. Okay, excellent. Good. So thank you. That's very helpful. Good. So I've got a sense of where we are here. That's good. So I'm going to move into the body of the presentation here and visit the archetypal esoteric programming language, which is called Intercal. So this was invented in the early 1970s by a couple of computer science students at Princeton University, and really it was a parody of the verbose and unwieldy imperative languages of the day. Think Fortran or COBOL or similar languages. Instead of the then universal go-to statement, there was a come from statement. So you encountered a label and then you went to the place where you should come from when you see that label. So effectively it's kind of the reverse of the control flow edge for the go-to. Imperative statements may be prefixed with the modifier please. But if you say please all the time, the compiler tells you that you're fawning too much and, you know, you're kind of a bit woolly, a bit weak. So you shouldn't say please too much. But if you never say please at all, it tells you off for being impolite. You should roughly say please between half and 2/3 of the time, I think, generally. Like Perl, variables are prefixed as to whether they are scalars or arrays, or I think this colon here indicates an array, and this is an assignment here. The struck through C symbol, the cent here, is a bitwise interleaving of these two constant values, that's 0 and that's 256. That's fairly normal. So you kind of interleave those bits together. Not very interesting because only one bit to set there, but you could imagine more interesting ones. And when you get to the end of the program, you denote the end of the program not by returning 0 from main, but instead by saying, please give up. And that's the end of the execution. So this was quite a joke of a programming language, but it was accompanied with a real implementation, a compiler that actually ran on their hardware in Princeton, and also a fairly extensive manual. So this was a well-documented programming language. Bratishenko coins the phrase techno-masochism to describe intercal philosophy. The idea is that programmers somehow experience pleasure from the pain of writing in this very difficult programming language. And one person who was techno-masochistic was Donald Knuth himself, because he records writing a program in Intercal, and he documents this in Selected Papers on Fun and Games, volume 6 or 7, I think. If you like the look of Intercal, thanks to Eric Raymond, there is a C language implementation of the compiler and the runtime, and you can just apt install it on Ubuntu or brew install it on your MacBook, although I think it only works on legacy Intel Macs and not on ARM Macs, which is very sad. The compiler is called IC, and it comes with even more mysterious error messages than, say, GHC or other compilers. So here I've got syntax error on line 1. No skeleton in my closet, woe is me. Correct source and resubmit. I think that's a deliberate typo. So I'm claiming that Intercal is the archetypal isolang because it's kind of defining the genre here with syntactic absurdity and this satirical stance towards conventional programming language design. So what I'm going to do next is somehow categorize the entire field of isolangs into 3 broad groups. Now, these divisions aren't necessarily disjoint, so there might be some overlap between them. But I'm going to claim that the 3 types of isolangs that we see at large today are those which have pseudo-natural language syntax, those which have non-textual syntax, and those which have, let me say, an unconventional computational model. And you can see immediately there will be some overlap between these because the first 2 relate to syntax and the third relates to the underlying computation. We've looked at the Shakespeare language already and seen how Elizabethan theatrical script can be interpreted as programs, and there are other similar textual esoteric languages. So 1980s rock lyrics can be interpreted as code in the Rockstar language. Recipes can be interpreted as programs in the Chef programming language. And indeed, it's possible to write a program that can be executed both in your oven and on your computer. And in one case, it makes a delicious chocolate cake, and in the other case, it says something rude to you. But that's by the by. And also there's lol code, which is some kind of internet meme chat thing. And here's some examples here. So this is an assignment statement. All these languages. Thou art a red rose. We saw that in Shakespeare. Rose is 1. Red multiplies it by 2. Let your love be 2 is apparently assigning the value 2 to the variable love here. 2 grams of chocolate. And this, again, this is stack-based here, assigns the value 2 to this chocolate stack here. I has an R, X R2, apparently is X : equals 2. And then you can print these things out, opening your heart, shouting your love. Serves 1, I'm not sure about that. That's in Chef. And visible X, there we go. So these things, you know, you read them, and they look like nice songs or plays or recipes, but actually there is structure hidden in the implicit in the text that can be interpreted by one of these generally stack-based programming language interpreters. We've seen non-textual syntax as well, like the white space language and the Pete language, which you saw there with its graphical notation. There are other non-textual programs as well. Programs can be written as directory structures in file systems. Where's my friend Joel? Yes, good. So I wouldn't have classified your language in yesterday's Onward as esoteric, but there are certainly esoteric languages that do things like that. Yes, so it's possible indeed. So here the syntax is written in extraordinary ways, and somehow the artifacts are unusual and the things that you wouldn't expect to be programs. Unconventional computation, I think the canonical example here is John Conway's Fractran programming language. There was a typo in the camera-ready copy. I called it Fractan. Sorry, it's Fractran, like Fortran. And Fractran here, you have a program with an initial input n, which is an integer value, and then a fixed list of fractions, and you execute the program by multiplying the integer n by the first fraction, which will give you an integer answer, and then you replace n by the integer answer and go round again. First fraction, which gives you an integer answer with a multiplication, and so on. You carry on until there's no such fraction and the program terminates. And this program here computes a list of prime numbers. And this is in the original paper from Conway in '87, Open Problems in Communication and Computation. And this is available on the Springer website. Here's another Perlis epigram. Beware of the Turing tar pit, in which everything is possible, but nothing of interest is easy. So you see, these languages could be, and often are, Turing complete, but to write an interesting program takes an awful lot of source code, because really the opcodes are so simple, and there's no standard library, and it's rather complex to do anything interesting indeed. Violetta Lenati, from a computer science education perspective, explains how programs can be viewed in 6 different ways. And these things pair up. So a program, for instance, is both a human-made artifact and yet also a tool that does something when executed. It's both an executable entity, you know, you can run it, and also a notational artifact, you can just kind of look at it. It's something that's abstract, and yet somehow something that's physical and embodied. And she speaks about how, depending on the way you express your program, depends on whereabouts in each of these different dimensions it lies. I'm going to claim that esoteric programs are generally more notational than executable, more emphasizing human manufacture than tooling, and probably more abstract than physical, but that's debatable perhaps. The point is that artifacts themselves are programs. Now, of course, not every artifact is a program, so you can't take the real text of, say, Hamlet and feed it into the Shakespeare interpreter because it doesn't have the necessary structure. There are often more than 2 people on the stage, and they don't necessarily say nice complimentary things to one another that could be interpreted as assignment statements. But it is the case that every Shakespeare program could be performed as a play in the Globe at the Royal Shakespeare Company and whatnot. Okay, so here is really the meat of my essay here. Why are we so attracted? What is the enduring, alluring appeal of esoteric languages to computer scientists? And I'm going to claim there are 5 reasons for this. First of all, a sense of fun or playfulness. Here's a quote again from Eric Raymond. "We hackers are a playful bunch. We'll hack anything, including language, if it looks like fun. Deep down, we like confusing people who are stuffier and less mentally agile than we are, especially when they're bosses. There's a little bit of the mad scientist in all hackers, ready to discombobulate the world and flip authority the finger, especially if we can do it with snazzy special effects." So somehow, inside each one of us is a sort of rebellious instinct. And that's expressed in our esoteric programming language usage, perhaps. Perlis puts it like this, and this is a quote not from his epigrams, but rather from the prologue to Structure and Interpretation of Computer Programs. He says, "I think it's extraordinarily important that we in computer science keep the fun in computing. When it started out, it was an awful lot of fun. I hope the field of computer science never loses its sense of fun." And I feel that esoteric programs are fun, and maybe your laughter and humorous engagement with the esoteric programs we've looked at so far indicate that fun, which perhaps you lose when you're grinding through a 10,000-line C# program, or whatever else you might do for your day job. You know, this is more exciting somehow, isn't it? More fun. Here's a second reason. This second reason is nostalgia. Here's Scotland's first digital electronic computer, installed at the University of Glasgow in the late 1950s. There's the first software engineer, and there's the first professor of computing over there, with a proprietorial hand on the RAM. Indeed, that is a mercury storage tube array that's kept at a very certain temperature. And, you know, in those days, and maybe when you started programming decades ago perhaps, it was just more difficult than it is these days. Do you know what I mean? Kids nowadays with VS Code and Copilot and things like that. It's just so easy, isn't it? You know, when I were a lad, you know, when I used to fire up Emacs and, well, I still do actually, but, you know, as things were back in the day, it was much more difficult. And when you were tracking down those, you know, unexpected bit flips and things like that, it was much more complicated, wasn't it? And I feel, and maybe you feel this too, the thought to execution ratio in software development used to be much higher than it is these days. And I think people have been saying that since Alan Turing, basically. You know, execution's cheap, debugging is easy, and thinking, who needs that? Well, I think you do with esoteric programming languages. Generally, you know, you have to think very hard and maybe write things down on paper as you write your esoteric programs. So perhaps we are harking back to those days when we had flowcharts on the floor and when we, you know, printed out memory dumps and looked at things and thought very carefully about what was going on. I'll read you a bit from the essay. It's rude about Americans, but sorry. It's often the case that experienced developers enjoy wearing the hair shirt, citing Simon Peyton-Jones, which involves putting themselves through difficult experiences while developing supposedly more elegant code. This trend originated with Turing, who invented the notion of optimal coding, whereby he would situate instructions at precisely the best locations in memory to be executed with minimum delay in a rotary memory machine. The pilot Ace had circulating mercury delay lines to store instructions, whereas other early stored program electronic computers employed complex control circuitry to avoid needing to make these instruction placement calculations. Turing wanted to defer placement complexity to the programmer. Campbell Kelly records Turing's thinking about using hardware interlocks to avoid the need for optimal coding as being, quotes, much more in the American tradition of solving one's problem by means of equipment rather than by thought. So Turing's saying programming should be challenging. Who needs electronics to help us decide where to place things? You know, we can live with our pipeline bubbles and our, you know, optimal encoding of delay lines and so on. It's, you know, don't defer to the compiler, optimize by hand. Here is a third reason for the attraction of esoteric languages, and this is a sense of cultic initiation. Here are the Pythagoreans bowing down to the rising sun, and, you know, there was a sense that they belonged. They knew about numbers, and they were the people. And maybe we too have this sense of belonging. We have been initiated into the cult of esoteric programming languages. It's certainly the case for natural language as well as programming languages that language functions as a social bond. You know, if you speak Klingon, come and talk to me afterwards, and we'll have a nice little Star Trek huddle in the corner. There's a sense of cultural identity, perhaps, isn't there? And I think a discourse community can engender that sense of belonging, and that's true in esoteric languages as well. To the novice programmer, unfamiliar syntax, an abstract concept can feel confusing and discouraging. By contrast, experienced programmers embrace this complexity, finding enjoyment and stimulation in the challenge. Esoteric programming languages foster a sense of community, a cultic initiation, an inner circle of programmers, engaging with code not just as a practical tool, but as a source of amusement, aesthetic pleasure, and intellectual play. A key point in cults and esotericism is the idea of transmission. You know, there's a kind of mystical way of becoming a part of the community. You know, thank you. I might say, here's a tarball of my latest esoteric language. And, you know, you're not going to get a Visual Studio plugin for this language. And, you know, you're not going to find a dummy's guide to learning this language in 24 hours, or indeed a Coursera module on this language. It's much more difficult to get into it, perhaps. Cultic initiation. There's artistic value as well, isn't there? Brooks talks about the sheer joy of making beautiful things. And Donald Knuth, again, talks about the art of computer programming. There's the idea of a thing being beautiful and somehow aesthetically pleasing, isn't there? We could think about live coding, for instance, where the coding itself is a performance. And here in esoteric programming, the artifact itself is a beautiful work of art. But then there's pedagogic value. So, you know, we teach people programming languages so that they can do computational thinking in some sense, but as they learn a new language in a reflective way, they somehow relate that back to programming languages they know already. And side by side, they compare how to do computation in these different languages, and that teaches them more, perhaps, about computational models and about computational thinking. There's the idea of appraising language characteristics, which we would want our students to do in a kind of manner of critical thinking, and they could be very critical about some of these esoteric languages. Most esoteric languages were written by computer science students. And I think it's nice to consider that a language that's small and self-contained could be written, you know, in an evening by an amused second-year undergraduate, or perhaps as a coursework exercise, or something like that. Many students undertake coding competitions like the Advent of Code. Does anybody here do the Advent of Code? You get 24 problems in the first 24 days of December, and you solve them in a language of your choice, and many people choose to solve Advent of Code problems in esoteric languages. Just search for Advent of Code in BF, and you'll find lots of interesting implementations and Git repositories there. Why do people develop esoteric languages? Going to very quickly talk about 3 reasons why this might happen. One is the comedic value of the language. And, you know, there is a bit of a joke to this, isn't there, really? The white space language was publicly announced on April Fool's Day in 2000 and something. And indeed, it was inspired by an April Fool from Johannes Strustrup himself, who spoke about how a certain dialect of C++ could be written in this kind of white space notation. There's a sense of challenge as well, and I think that's important, isn't it? The idea of working within tight, self-imposed constraints which I think is a skill that's valued by software developers and is very necessary in esoteric programming languages. The Malbolge language, for instance, is practically impossible to write programs in, and most programs in that language have been synthesized by some kind of search-based techniques. But it's good to sometimes write code with a straitjacket, and it kind of teaches you to work very efficiently and correctly. And then creativity. I think this is important, isn't it? The attraction of creating a programming language of one's own. Enjoying the luxury of a break from the bland, bloated, multi-paradigm languages with imperative roots that everybody else is using. Esoteric languages are probably designed for the pleasure of the language designer rather than the end-user programmer. But there is a creative urge, a juice in every one of us to say, that's my programming language. And it's much easier to do that with an esoteric language, perhaps, than a mainstream one that other people are going to use. Just quickly, related work. So, an interesting book was published just a month ago called 44 Esoteric Languages, The Art of Esoteric Code, and you must take this seriously because it was published by MIT Press. So, check it out. It costs 50 quid, but well, how many dollars is that? I don't know, $60, but that's an interesting book to have a look at. Some of his languages ask programmers to write code in the form of a prayer to Greek gods, or as a pattern of empty folders nested in some kind of file system. There are constructed natural languages as well. If you go to vulgarlang.com, you can create your own constructed language and specify the phonemes and the morphology of your language. Sometimes people joke around with other systems like chess, for instance. Chess 960 is where you randomize the back row of your chessboard, and there are 960 combinations as long as your bishops are on opposite colored squares, and you can still castle effectively. So this is a way of perhaps looking at a very familiar thing in a slightly different way. And indeed, there are joked musical instruments, and perhaps you've seen some of these, and these can be used in serious ways, perhaps. And I just put this in as a nod to the previous talk. Look at this. I've developed a new programming language. Didn't a judge order you to stop doing that? High Court throughout the ruling. Back, suckers. I promise it's good this time. Normal code, good clean syntax, nothing weird. Except the only variable name is x. To refer to different variables, you have to write x in different fonts. There's XKCD's esoteric programming language. I will conclude, and I'm going to say we must take esoteric programming languages seriously. They challenge conventional thinking in terms of both programming language design and the nature of programming itself. As Perlis says, a language that doesn't affect the way you think about programming ain't worth knowing. Thank you very much.
Out of time, but there's half an hour until the break. I don't want to have questions from it, but yes, there is a bit of time for questions.
Yeah, I was going to bring up constructed languages, and then you brought them up. So I guess have you ever heard of Agma Schwa's constructed a cursed conlang circus?
No.
Is basically like a bunch of linguists and all linguistic interested people like creating conlangs, which are designed to be cursed. And I think this is basically, so some of them do phonetics that are very cursed, but some of them are basically like, there's one which is essentially a hashing algorithm, and there's another one that's like from set theory. Like essentially it's just saying that you can use set theory in theory to talk about anything. So like, I guess, that might be something to look into.
Thank you. I will. Thanks. Yes, so constructed languages are interesting. I mean, from the days of Esperanto and things like that, people have reasons, and often laudable reasons, for constructing languages, and your reasons might not be quite so laudable, but we'll look into it. Yes, thank you.
Is the lambda calculus an esoteric programming language?
Good. So, I think I'm claiming languages are esoteric when we consider the motivation of the designer, and I don't think Alonzo Church was intending his language to be used in humorous ways.
I like that answer.
Yes.
But of course, there
However,
are Oh, go ahead, you're for yourself.
Sorry, however, I think you could fall into the Turing tar pit trying to write an interesting program in lambda calculus.
Well, there are isolangs that are just combinator calculus but realized, and then those become isolangs when combinator calculus is researched. So what's the difference?
That's nice. Thank you. Thank you. Yes.
I wonder if you know of any concepts that were introduced initially by esoteric languages that have entered the mainstream and influenced the field.
How nice. So often when I'm teaching Haskell to my students, I say, and here, look, list comprehensions are now available in other mainstream languages and things like that. Is that true for esoteric languages? Sadly, I'm not aware of anything, but I should think about that very carefully. Yes, yes. Give me an example, James, please. Yes. Yes, yes, yes.
Thank you.
I think that's said with tongue in cheek, but yes, yes, very nice. Thank you.
He got
a lovely point, Nick.
He got my question, but
Oh,
I do have an answer. I do have an answer to that,
Oh,
which is that,
please.
if I remember correctly, there is a commercial COBOL that had come from. It
Really?
exists. It's real. It's out there. I'll just say this. I think it's very funny. You know, obviously, you know, Wittgenstein said, you know, we could conceive of a language composed entirely of jokes. I don't think he could have foreseen that that would literally happen in the form of programming languages. But yeah, I'm 99% certain the come from COBOL exists.
How lovely. Okay, we'll check that out too. Thank you.
I have another answer to that question, which is I remember a programming language that was like, oh, usually the compiler parses your code and ignores the comments. And what if you had a language that parses your comments and ignores the code? And I think with modern Copilot tools, we're there. So.
Very good. Very good. A truly literate program. Thank you. Thank you. Very nice. Good. Thank you.
will be given by James Noble about exploring the very faithful runtime enforcement of dynamic capabilities. If we are ready, then let's start.
Excellent. My wife in New Zealand, and I did mention that I wasn't really sure whether I'd finished my slides in time, and I thought, well, I could always pretend I was Sriram and then just facilitate a discussion for half an hour. And given that Jeremy managed to basically fill this room with people for a discussion of languages like white space and brain fuck and the Shakespeare thing and intercal, and I think that probably would have been a better choice. But anyway, these pictures were generated by ChatGPT. The actual pictures of actually us are here. Yeah, and anyway, I'm sort of going to be talking about exploring design space for runtime enforcement of dynamic capabilities, which is work being done by the big guy here, Andrew Fawcett, who, for family reasons, couldn't be here. And this is very much his work, and I thought this would have been an excellent topic for him to present as, the sort of first debutante coming out presentation as a PhD student, but he couldn't be here, which means I've got the luxury of a half-hour slot to fill, perhaps with not much content. Anyway, we shall see. Oh, yeah, you know who this is? For those of a certain age, Yosser Hughes. Yosser Hughes was a famous character from Boys from the Black Stuff, a 1980s British TV show, who was going around saying, "Giz a job," and that's there because I'm saying "giz a job" because I have been working as an independent researcher, but either I need another research contract or, a job. Anyway, and I said, should I put the "giz a job" in there? And Tobias says, of course you should. So anyway, there's nobody here from Jane Street in the room, so I'm probably screwed. Right. Other things happened in 1981 other than Yosser Hughes saying "giz a job." There was the ZX81, which actually was the first computer that I owned, which I was able to pay for from my... It's going to be relevant, kind of. Relevant. It's at least as relevant as the joke I made about Lolland's language at the start of Jeremy's talk. The ZX81, I was able to afford that with a paper round, and it came with a number of interesting features. Well, really only three. A wobbly RAM pack that fell off, a really dodgy link to a television, and a cassette interface. 1981, okay? And I used that. Actually, I did get slightly better versions of the ZX81, but when I got to university in the mid-80s, we actually had, well, in fact, we had knockoff cheap versions of these VT52 visual terminals, okay? And then the other thing, of course, that happened in 1981 was IBM, produced this, the first IBM PC with a whole 256 kilobytes, or maybe it was only 128 kilobytes of interface, and you can see it's got a printer and it's got space for floppy disks and a cassette interface. Not many people know that. The first PC had a cassette interface. And by the second sort of generation things, they stopped pulling the cassette plugs out to the back of the case, but circuitry was still there on the circuit boards. Anyway, maybe this will be relevant. We'll see. Also in 1980, and it's like in another effing world, this was going on, right? Byte issue of Smalltalk, that's Smalltalk 1980, programs writing like this, and you couldn't... There's a different talk when I argue that the ZX81 is perhaps closer to Smalltalk than you might think, and certainly closer to Smalltalk than the IBM, at least the IBM PC running the standard operating system, although PCs were shipped with, was it 3 or 4 operating systems? One of which, USCD Pascal, was actually a hell of a lot closer to Smalltalk than you might let on, or Scheme. Anyway, that was Smalltalk, but at the same time, if you had a lot of money, you could have that, if anybody knows what that is. It is a standard screen grab from the Xerox Star. The Xerox Star, which was the first effectively commercially available thing with a graphical user interface. But you're wondering what that's got to do with concurrency? We'll get there. That apparently cost $75,000 US and was hulking great. As somebody said, it was something the size of a fridge. It ran on a bit slice processor, which, strange as it may think, basically it meant, I think it was 16-bit machine, so it had effectively 16 1-bit processors that all worked in parallel, and each processor... Anyway, never mind. It's ridiculously cool stuff. And there we go, and that was 75,000 US. They figure, in inflation in Singapore or New Zealand dollars, that's about $500,000 just for one of those to get it. Believe it or not, at the same time, of course, Apple was producing that, if you know what that is, and I've decided that is actually a trick question. It wasn't supposed to be a trick question, but it is. Anyone? It's a Lisa. Well, that's right. It looks like a Lisa, the Apple Lisa. There are two. Apple really only made 4 computers. The Apple II, there was an Apple I, we don't mention that. It was the Apple II and a whole range of those things. The Apple III, which I had the misfortune of having to use, which also came out about 1981, and was their thing that they were kind of finding the IBM PC on the cheap. The Lisa, and then of course the Macintosh, which we still have today, kind of. But that is a Lisa. Well, it's not actually a Lisa, it's a Mac XL. Because when, in 1984, the Mac came along, it basically blew the Lisa out of the water. It was cheaper, it was more portable, and so what they actually did is, you can see this has got the 3.5-inch disk drive. The original Lisas had 5.25-inch disk drives that didn't really work, but you can actually see that's running macOS, or a hack version of macOS. If you've ever used it, it's horrible, because one of the big things about macOS was the pixels were square, but here the pixels aren't square. They were vertical rectangles, because that was how the Lisa worked, because they thought that's what you needed for getting high resolution for document production. This thing was, I think, something like 10,000 American, 60,000, so 10 times less the price of the Lisa. Sorry, of the Xerox Star, and then the Mac came along, and here's what we start getting to the point of the talk, or I've wasted the first 10 minutes. That was my plan. Advertised as the computer for the rest of us. The computer for the rest of us. Because, you know, that thing cost $1,000 US, maybe $2,000 New Zealand dollars, maybe a bit more when it first came out. Sure, it was only 128K, and sure, it had some of the most sophisticated machine code ever written. In fact, it probably did have the most sophisticated machine code ever written for multiplexing floppy drives. Because it really needed 2 floppy drives, one for the system and one for the application data, or possibly the application program. And it had a memory manager built in that effectively gave you virtual memory on a 68,000 backed by floppy drives for your source code, but it could also actually store out RAM and back again. And you know, you would call load a segment to load in a chunk of your program, and then it would go and find the floppy drive. And if, because you bought the cheap one with only one drive, the right floppy wasn't in the disk, it would sit there and say, would you please insert this other disk? And you then insert the other disk, and you waited while it crunched. What's this got to do with concurrency? Oh, we're getting there. If you look on the jargon file, if you look up for the rest of us on the for the rest of us on the jargon file, it says it's basically, you could think back to what Jeremy was talking about again. It's basically there's this entry here for the rest of us, and hackers have this piss take on that phrase for the rest of them. So whereas we can, you know, get in with soldering irons or COBOL or Intercal or machine code or higher order type theory or le roc, le programming language française, perhaps, you know, the Prologue or Elgol or Eiffel or something, whatever these strange. Are there German programs? I don't want to think about that. There aren't any German programming languages. Plan calcul, yeah. I should say jawohl at that point, shouldn't I? Well, anyway, that remind me not to apply for a job. Remind me not to give this talk and make those jokes if I apply for a job in Munich. Anyway, look, they've got a much more sensible attitude than people losing control of their right arm while addressing a major political rally, I think, in Munich today than they do in freedom's land and bravery's home. Right. For the rest of them. And here, you know, sorry, I carry on, used in reference to software or anything which doesn't provide obvious capabilities because it's thought the poor losers might not be able to handle them. The rest of them, yeah, it's an attractive design of the rest of them, you know, they're stupid, blah, blah, blah. There's an awful lot of contempt because, you know, really, you should be a real bloke. You know, Paul Hexeth's kind of programmer without a beard. Programmers can't have beards, and they've got to wear proper shoes, and they've got to stand up straight, and got to be able to do the hard things. Yeah, right, fly the drones. You have to be very physically fit to fly drones. Not many people know that, you know. Sorry, you can't fly drones if you're a woman or a non-Christian. Quite how that works, I'm not quite sure, really, but anyway. So, I've been told I should tell people and try and get at least one big point across in the talk when I give talks, because then I talk to people a few months afterwards and they tell me what they think I told them, and it was nothing at all to do with what I wanted to get across. So, and Sophia's, anyway, Sophia's had to sit through many of my talks. She regularly experiences this. So, why I don't think this has been a terrible waste of time, and if you take one thing away from this talk, this is what I want you to take away. And in some ways I'm being really mean to many of the people in the room by putting this up. What's concurrency for the rest of them? Okay, what is concurrency for the rest of them? Because that is the underlying motivation for this project. And in a world in which JavaScript is apparently quite seriously planning to adopt all the ideas that were the best in when? About 1990, when we had them in Modular 3, and that were then copied and put in a language called Oak that was renamed Java in terms of concurrency. And 25 years later, we're now thinking of putting those things into JavaScript. And when apparently, according to Tobias, I've mentioned that, apparently Python thinks that would be a good idea too. May Milano, who isn't here, has got really interesting stories. At least the Swifties, in some ways, are pushing back on some of the weirder stuff we would like to do. So that's the idea around which this particular stream of work, if I can discipline myself enough, which generally I can't, is trying to get up. What is concurrency for the rest of them? Because, whether it's ChatGPT-3, I'm sure that's really good at doing concurrency, or whether it's just programmers who have got a degree, or maybe they've been to a polytech or a trade school and have learned to program and are now faced with doing concurrency, what do we tell them? And I still maintain, whether it's Swift, or whether it's Rust, or whether it's OxCaml, or whether it's Rock, or whatever it is, Forth, or even Smalltalk, I don't think we've really got very good answers. Maybe there aren't any good answers, I don't know, but this project was an idea to come up with one take on that, and you'll kind of see where we get to at the end. So now I'm actually going to start on the students' talk. Here we go. This is actually, that's the headline from a different paper for the overall Dala project. The idea effectively was done by Kiko Fernando Reyes, who is not here. He was here, no? He was here, but he's not here anymore. He was that's right. He is now the god of concurrency at Erlang, and he basically tells them not to do anything fancy, I think, and just keeps doing this. And a bunch of other people, most of whom, but not all of whom, were either at Vekor at Uppsala. Concurrent programming is hard, blah, blah, blah. There is a version of this slide that I couldn't find, which at this point, all the little Dala horses start flying around on the screen, so you can imagine that happening, so you can't actually pay any attention to what I'm saying because you're being distracted by all these different things happening simultaneously. Very much like if you're chairing a session at, I don't know, Onward and trying to finish your slides at the same time, while trying to work out why your Daphne program isn't verifying. Anyway, God, why do I have the next slide? I don't know. Concurrent programming is hard. Why is it hard? Well, we kind of need these things to be correct, and probably most people in the room would agree with that. Simplicity, well, I guess once you start saying for the rest of them, whether it's simple or not and what that means, in fact, is actually a difficult thing to say, but it would be nice. And Doug Lee always points about performance. And he says two depressing things about performance. The thing that's depressing, particularly for the functional people, is assignment is always faster than copying. It just is. It's this thing called physics, entropy. Writing to one word in memory is going to be more efficient than copying megabytes, gigabytes. And the other thing which is really depressing for all of us, he says, is, well, why are you writing the concurrent program in the first place? Why are you writing this concurrent program in the first place? I mean, is it just because you like having the CPU meter high? Is it because you like burning your battery life? I mean, you can always get high utilization when you evaluate your programs, but what's actually important is throughput. In other words, your program actually needs to do more work in less time than it would take if you just wrote the sequential program. Because guess what? The sequential program is going to be, it's always going to be a hell of a lot simpler than the concurrent program, and it's more likely to be correct. So if we as programmers are going to waste our time or spend our time or get our LLMs, if you're that way inclined, you know, you're under the age of 20, well, according to the YouTube ads, under the age of 40, and who doesn't know how to use ChatGPT-3, and so I'm not asking it to write my Daphne code for me, it's always going to find writing a sequential program easier than writing a concurrent one, pretty much. We can talk about the others afterwards. And so if it's not performant, then again, what's the point in doing this? We may as well just let people write their basic programs or whatever it is and be done. So what does this come into? So the idea for correctness is what we call the Dahler model, which is very much a hypothesis. It's not something I believe. Or maybe it is, I don't know. For simplicity, we had this excuse that we will try with gradual types. We're a long way away from that. Although, once again, we're actually going to touch on that. And for performance, our hope was that we would do this using MetaVM techniques. So things like Graal, at least until, when was it last week that Oracle, whoever it is, Larry Ellison decided to spend the money on yachts instead because he wants to be able to beat New Zealand in a yacht race because we're such a large and important country. Okay, so what's our take on doing this? Well, we're going to say capabilities for dynamically typed object-oriented language, blah, blah, blah. Okay, support for concurrency. We're not really ready to commit to a single model of concurrency. I think there's either probably another Dougley or Alan Perlis quote that says, every model of concurrency is wrong. But we kind of feel we have to commit, really, even if we don't really know what it should be, because we have to make progress somehow. We have to come up with some kind of ideas. And what we would like is, along with everybody else in the whole world, to guarantee some sort of data race freedom. That seems kind of important if you want to say, well, what's a good description of what a language is that in some sense is concurrency safe, then you may as well go with data race freedom. Again, for the people who are pushing, disentanglement, which I think means, someone can tell me afterwards if I'm wrong, no data races in the memory allocator, which apparently is a big thing in Haskell, but every other language has had per-thread allocators for probably decades now, so it's not so big in the real world. Anyway, okay, so that's what we're sort of after. For some reason, there's another build. I don't know, there was a little pink horse appearing. Long-term gradual typing, okay, we're a long way away from that. So if you want a second takeaway slide, it's probably this one, which has adorned many of my grant applications, and enough of which got funded for me to still be here, which is why I was only doing the gizzard job slides now rather than 3 years ago. The idea is we're going to coordinate these objects into three what we call flavors, because I watch too much physics YouTube when I'm waiting for my Daphne to verify. And those three flavors are ISO for isolated, im for immutable, and local for local. Which means pretty much what you think they are if you've done any kind of this. There's possibly another flavor that will appear shortly, but that's the main thing. And the point is here, there is this ownership structure or stratification or whatever you want to call it in this model at this point, which says immutables can only point to other immutables. These things are, values, whatever that means. Shout out to Dimi Rakordon, who isn't in the room, but if she was in the room, she would hear me say, look, there are these values, and she's actually done some interesting work on it, and there was a couple of papers she talked about. Values. Then there are local objects, which, well, they're kind of like thread local objects, not thread local variables like they have in Java, but objects that are going to be confined to a thread. Great, and once they're confined to a thread, you're basically doing sequential programming, but they can refer to other local objects. They can also refer to immutable objects. Have I got this the wrong way? No, I've got this the wrong way, haven't I? And then the third type of these ISOs. And ISOs can refer to immutable objects, but they can't refer to thread local objects. Right, okay, that does make sense. And so the point of ISOs is these are isolated in the sense that Peony or other things are isolated, or if you take the right drugs, you can even see Rust mutual objects as kind of being isolated in the sense that we kind of, well, to quote Tobias's thesis, external uniqueness. You can only have one pointer into this, and that pointer to ISOs can come from an ISO or it can come from a local object. There's an interesting question about whether we should allow immutables to point as ISOs, but that's pointless because, no, we can't allow immutables to point to ISOs. And they don't in my diagram. I was just thinking, could you get away with it? Because there'd be no point because you can't change the pointer to an immutable thing. So the point of ISOs is because you know and have control of the sole incoming reference, you can then hand these off to different threads. And because they can't only point to ISOs, the ISOs will go with them. Because they can point to immutables, the immutables are just out there in the, the Haskell universe, Haskell universe. I guess we've got a Herbrand universe. We've got to have a Didier universe for functional languages. So the Didier universe of all these values, and you can refer to them. But you can't refer to thread local things because you might be moved to a different thread. General side where I make a snide comment about Rust. We can take that as given. So basically these slides just sort of put this all together. Forget what the color coding is. I guess immutables can point to them, and then you can have... Oh, blue is... I don't know. You made those slides. I just stole them. Anyway, you can basically... There are these rules about what can point to what. How we work out, or on this one, yellow is local, greens are ISO, and blues are immutable. So I was right. I was going to say these things are immutables. And then they can be pointed at by the ISOs, and then in the end, you've got the locals kind of sit at the top of this particular tree. Or tower, I don't know, stratification. There must be some universe, object universes. There we go, right. Some versions of paper then have another one, which I kind of like ignoring because remember that bit I said about concurrency for the rest of them? This is unsafe object, which I'm really going to try and ignore for the rest of the talk, but it is there if you want to read the paper. It just makes things worse. That was the original version of a slide for various reasons. Again, because I've been watching too much quantum physics and because even I have trouble trying to work out what the difference between a capability, a reference capability, an access permission, an object capability, whatever a capability bit is. I'm trying to discipline myself, not entirely successfully, and I have completely failed to discipline my student into using the word flavor, or at least I'm trying that out to say the objects have flavors. Other things might have capabilities or other things that constrain what flavors they can address or what they can do, but objects have flavors in this system. We all know what a data race is. You still want me to finish half past, yeah? Okay, all right. What does it look like? Well, we'll get there. We will get there. What does it look like? Code kind of looks like this because it's based on Grace, which was the language that myself and Andrew Black and Kim Bruce claimed to be producing for educational reasons. And it's not that we've given up, but that COVID came along and then they retired, and I kind of had a different research project to do in order to feed my family. And as I at least said at the time, 15 years ago, God, when we started it, that we said it was an educational language because if we just said, look, we're just kind of do a minimal object-oriented language, everyone would think we were crazy. These days, I would be trying to sell it as, well, it's kind of like a gradually typed version of OCaml. But I'd only describe it that way because OCaml was cool. But if you go back and look at the papers, it does point out that, in fact, there are a lot of things which are very similar in Grace to the way that OCaml does. And it's not accidental that it looks like, it looks quite a lot like Scala, except we don't say deaf because, we are deaf to the record. Sorry. Have I made a Flavor Flav? No, I haven't made a Flavor Flav joke. Right. On this slide, you can see we're binding ISO. That object there, var account is going to be an object which is ISO, but branch, which is basically just an object with a name, is an immutable, and we can just do kind of stuff with that. The theory is anybody who can read anything from Java or certainly Kotlin on upwards would be able to read Grace without even noticing that they were reading Grace, and more to the point, would then pretty much be able to write it. So, the rest of the paper. So that's that so far. That's the Cordala model, but of course things are never that easy. So the rest of the paper basically looks at 6 different axes of the problem comes when you actually try and build something to do this. So we're going to build a dynamic language to do this, which is what we wanted to do. And the questions are kind of like, well, when are particular things enforced and how are they enforced? It's not just enough to say, well, quoting Hitchhiker's Guide to the Galaxy, it's not just enough to say, well, we want fire, but as Douglas Adams put it, well, do you want fire that can be fitted nasally? If we want, say we want an ISO, the question is, well, when are we allowed to use it, and what does it mean that we are actually ISO? So the paper looks at these various alternatives in this axis. So, for example, the staunchest one, which says every time you do with one of these things, you've got to explicitly do a destructive read. In that case, you write this first line and it will crash because var y is reading x, x has got an ISO in it, you're not doing a destructive read. After that, you're left with two variables, same scope, pointing the same thing, bang, you're dead. Another option says, well, maybe you could do it when you do reference something. So we will let you do borrowing, which, if you've been to the talk I gave 3 days ago, doesn't actually exist, but for the purpose of this talk, it does. So you've kind of got this borrowing thing going on, but when you actually try and use an object in any way, at that point, you would kind of kill this thing. You would try and send a message here. And one way to think about it is your VM would just check the reference count on Y, and the reference count on Y isn't 1. So it crashes and said, you are trying to use an ISO that has 2 references. Please find one of them and kill them. And if you think that's worse than the Rust error messages, I couldn't possibly comment. And so, going on, there's basically a bunch of these things. What does it mean to move an ISO? When do you actually do it? If you have an ISO that can move, because that's the whole point of these things. But when you actually consider that the object has actually moved, especially if you are in something that allows borrowing, how do you decide if the thing is no longer borrowed but is actually moved so it can now be accessed from the other thread? And there's a particularly twisted option there, newest, which I don't want to say, to me, feels a bit like what Rust tries to do, which is, we'll let people write the code and we'll get the most permissive interpretation of what their code could possibly mean, which in this case is you can always use the newest reference, but when it goes away, you can use the next newest reference. And if you think again about Rust borrowing, that's not a bad, well, that is a dynamic analog of what's going on there. Hopefully putting it down this way, you might think why it's horrible. And again, we can look at examples and say, well, this thing will crash under some semantics and won't under others. There's a bunch more of these things I'm finishing up now. Really, I am. About when things are immutable, about where objects get their flavor, and flavor change. Whether an object originally, we didn't think they could change flavors, but some people are keen on this. And so there is a version of this which actually gets you flavor oscillation and superposition and observer dependence in your programming language. Remember what I said about what the aim of this project was at the beginning? For the rest of them? Right. Anyway, I'm going to skip through all that. The paper goes on to say, well, look, what the student has built is, I think, these 5 variants, which he thinks are reasonably coherent combinations of the values on those axes. You can read the paper for more. If you're interested in more, since people are coming in to talk to a talk that has content, there is this definitely one way we can expand this, is where we'd have more flavors. We can have lots more flavors. There are jokes on that slide. I particularly like the last one there. We're scientists. It don't have to be, lose control of our right hand, but the student is actually building this on top of GraceKit, which is our, nth generation low-effort Grace implementation. There was actually a paper about that in MPLR that some people actually liked. And the student is going to go on and do various kinds of evaluation of that. And I put empirical tests in the quote because this is the other thing that people take away from versions of this talk, which isn't actually the point of this talk, but it is the point about why I don't think it's very easy to do empirical student-led or program analysis of these things, which is if you test these kind of different language options with people, what you're testing is the people, not the language design. If you test this with people who learn their concurrent programming in Rust, they will expect it to work like Rust. If you test it with people who learn it in Java, they will expect it to work like Java. Whatever, for whatever languages you've got. Coming to the end, if you remember Yosser Hughes, given that I'm begging for a job, remember how the actor Bernard Hill ended up? He ended up as King Theoden. He was also captain of the Titanic in Titanic, which is pretty damn good for a guy begging for a job. So I'm still maintaining my hope. Put perhaps this model somewhere in the back of your head. I probably would now say this is much more simple than what I would like. In some ways, the kind of experiments I'm hoping the student to do is actually to try and write examples of exemplary or kernel concurrent Gala programs and actually see what idioms are best expressible in what set of conditions. I think that is actually it's qualitative, but it's more useful evaluation than saying we gave it to a group of students, they figured out which version of the language we, as their lecturers who were marking them overall, liked, and told us that one is the best. Sorry, I'm cynical showing through. And again, most important thing from this talk is remember this. If the Macintosh was the computer for the rest of us, some of us do need to think about concurrency for the rest of them. Thank you very much. Sorry. There was a handheld mic as well.
Very interesting to me, at least, that there are so very many variations for each of the features that you were considering. Are there any that have not been implemented in languages that you came across because you were investigating? For instance, the one where you allow the alias to the ISO, but you throw an error when you try to call a method on it?
Given the wide swathe of concurrent language design that's been done in the last 30 or 40 years, I think there's probably even weirder stuff out there. I can't necessarily say that I can point at each of the ones we've picked. But it wouldn't surprise me if we had, and it certainly wouldn't surprise me if there are other semantics there that we didn't get. We're not trying to be completely, well, not trying to be completist, not at this point.
Okay, so
thank you.
Will be given by? Come on. Okay, so thank you for the introduction. So what I want to talk about is sort of a bit of a pet project that I've been doing on the side of my research that's motivated in a sense by a sort of pet peeve. But before going into it, I want to give a disclaimer. This is not science, right? This is not a study, there's no data, this is just an idea. Hence why I call the paper a manifesto. It's a sort of intent. And what's even worse, it's not even a new idea. Other people have said things sort of to the same effect or done things to that effect in the past. But I still think it's worth saying because, in a sense, to me it feels like an obvious thing, and I don't understand why it's not the thing that is done. And so I thought, I would at least write down what I thought and at least try to make a coherent argument for why we should try to do that, to see, or to be in a position to test whether it actually helps. So I'll give a little bit of context. So when I was doing my PhD, my friend Fiona said, oh, you should go and volunteer with Cambridge Stimulus, which is a thing that takes sort of PhD students or students and sends them to local primary schools to help. And the thing that I ended up helping with was a so-called code club at a local primary school. And in the context of that code club, what we used was the Scratch programming language and the code club curriculum. And I'll explain why these two are relevant. And so educational programming languages and I think the same conclusions apply to all of them,
or at least most of them. Now, I want to talk about a problem, but maybe before that, it's worth talking about sort of things that go well. So one thing that's really great about this approach, the sort of Code Club approach, is that it's project-based. And so what the kids do is, or what it has them do, is write small video games in this very nice integrated development environment. And it's really integrated. You know, you're running your game inside your IDE. And it's really empowering. Like, the kids love it. They like what they make. They think it's cool. They can show it to their friends. Their friends think that it's cool. And it's really, like, they're really gripped. And I think, you know, in a sense, programming is the closest thing we have to magic. Like, you know, words have literal power over matter. And I think they really experience that sort of fascination. It's like, wow, I can make it do that. So I think in that respect, it's very well. It is very good. But there's one observation we can already make, which is that these little video games, they're sort of a very specific flavor of programs. And they're typically very, very different from the programs that you and I write on a daily basis. And I'll return to that, because that's a very important point. Another thing that's really good with Code Club and Scratch is that it's pedagogical. Like, you have clear, well-explained guide that for each individual project that sort of teach the kids how to program. And, you know, they drag and drop their blocks, and there's very good explanations of, you know, why different things are needed, why different things help. Another thing that's really great is the sort of incrementality, because, you know, you can't really ask a kid to sort of drag and drop or type, you know, 100 lines of code. It's just way too much. They would give up way before that. So one thing that's really good with Code Club is that sort of instructed to write a program incrementally, where even a partial program is interesting, and you sort of incrementally refine it and add things that make it more exciting. And because it's, you know, block-based programming, then there's never like a dead lump of code that doesn't run because of, like, you know, there's a syntax error on line 43 where there's a missing colon or something like that. You know, the program is sort of always there and always doing something. Yet another thing that's really great is the UI. And I want to talk about that because I think it's really important, because, you know, I'm talking about this aspect that I want to improve, but I think at the end of the day, the UI is like 10 times more important than any PL aspect of this. And so I remember we switched from Scratch 2 to Scratch 3, and like the kids, when we changed, they were like, their minds were blown. Like, the fact that it was so much better looking for them was such a dominating factor. So, you know, at the end of the day, I know that my contribution is at best very modest. But yeah, I still think it's worth thinking about it. And the final thing that's really great is there's customability, and in particular visual customability, right? The kids, they can make their video game, and you can have, like, I don't know, a cat chasing a mouse, but then you can decide, I don't like the mouse, I want to replace it by, like, a dog. And you can just do that. You know, I don't want my cat to be orange, I want it to be green, and they can do that, and it's very easy, and it's very empowering, because they can make the changes that they want. You know, the instructions tell them, oh, put a cat, and they can go, actually, I would rather have a hippo. And then they put a hippo, and it's like their game. And it sort of reinforces that feeling of, like, personal investment. And I think it's very helpful. But there's one thing that's not so great, which is, what if you want to customize not sort of the visual aspects, but the mechanics of your little video game? And then the story is not so great. And Code Club often has, for projects at the end, there's like oh, what if you want to take it further? And then they give some suggestions that are sort of more open-ended. Like, oh, you could try to do that, but it doesn't necessarily give you, like, step-by-step instructions. But what kids want to do often is they're like, I have my little base game, and I want to take it in this direction, not the one I've been told, but, like, I want to tweak the mechanics somehow. And the impression I got is that often they hit a sort of expressivity wall. They have an idea of how they want to change their games, to make it do something else. And they can say it in words. They can explain it to me, who's trying to help them. But the programming language doesn't really allow them to do that. And I'll explain in more detail the sort of problems that I think I've noticed. You know, I've seen it enough times that I get the feeling that there's a pattern. And the experience is when they hit this wall, they get very frustrated. They're like, why can't I make it do what I want? And they feel very, very unhappy and annoyed, and then they give up often, I think, in the face of this frustration. And I think that sort of looking at these problems that they encounter with my sort of programming language theory background, then I kind of get the impression that these are artificial problems. They're problems caused by the language, but they don't have to use a language that makes them face these problems. I think we can do better. And maybe what I want to sort of make a bit more precise is the way I think the problem occurs is if you're trying to describe programming languages, this is like a broad stroke categorization. It's not a binary thing, but often you can categorize them into transformational languages, which are the languages that I guess most of us use most of the time. And this is things like Pascal, like Haskell, like whatever. And these are languages that are really designed to take an input and turn it into an output. And Scratch and other languages use this kind of language. Scratch at the end of the day is basically Pascal plus top-level handlers for a bunch of effects. And this is the languages that we're sort of most used to. But there's another category of languages, which are so-called reactive languages. And here the idea is not so much this sort of input-output relationship, but it's more sort of dialogue between the program and its environment, where there's events coming outside, and the program sort of decides what to do and reacts to that. And there's a sort of subcategorization of that, where synchronous languages are those that are sort of very concerned with the notion of time. And my thesis is that Scratch should use a synchronous language, because I think by switching to a synchronous language, then the kids will be able to express what they want more directly. They won't get so frustrated, and so they'll be more keen to program. And I think in a sense, merely by writing this down, it's kind of obvious that there was going to be a problem, because these little video games, fundamentally, they're not turning an input into an output. They're really about reacting to either external events, like someone presses on the up arrow, or internal event, like a ball hits a wall, or something like that. And so I think to try to support this argument, I'll give you sort of informal ideas of the kind of problems that I got the impression that the children faced, and then explain why I think synchronous languages solve this. So the first thing that children want to do quite often, and this is a thing that's very sort of natural from sort of both the video games that they know, but also everyday life, is this idea of level or phase, right? So, video game has levels. So you could have a very simple video game where you have like a cat and a mouse, and you have code for the cat and code for the mouse, and then the code for the cat sort of makes the cat move towards the mouse, and you, by moving your cursor with your physical computer mouse, you decide where the mouse, the sprite on the screen goes, right? And you can imagine you run that until the cat touches the mouse, and maybe you have a timer telling you how long you've evaded the cat, right? But one thing that kids often want to do is sort of, okay, well, I want to do a level, I want, when the cat catches the mouse, then we do something else. So for example, maybe they reverse role, maybe now the mouse chases the cat, something like that. And this is a notion that they're very used to, both from video games. I think they can express what a level is, but also from everyday life. They know that when they're at school, they're supposed to listen to the teacher, and then like the school day ends, and then they go on the playground. So there's this idea of a phase, like a division of time, is a thing that they know and that they can express in words. How do you express that in sort of Pascal plus top-level event handlers? Well, it's easy. You just add a turn variable, and then turn can be 0 or 1. And then, if turn is 0, then you do the code for the first part, and if turn is 1, then you do the code for the second part, and then somewhere you have some increment of that turn. This works. It's absolute spaghetti code, It's code that I don't want to write, but I can write it because I sort of have the mental model of, oh, at the end of the day, this is just an automaton. I know automata theory. I can just, encode it. I can think of my program, a transformational program, as like a function that takes the previous state and the action and determines the next state. Right? And if you program like Arduinos or whatever, this is the normal way of programming these things. But the thing that allows me to do that is this mental framework that I have as an adult, and also in a sense, the patience to go through this extremely painful encoding. And then not only is it painful to do, it's also painful to maintain. And also, when you're doing that transformation, your code is basically, in a sense, not compiling. Of course, it still runs, but it's like it's behaving weirdly and incomprehensibly, and the structure of the program really doesn't help you. And my point is, this is like absolutely not necessary, right? The language forces you to do that, but we all know programming languages well enough to say, well, you can obviously have in your language a way to sequence concurrency. So you can have, the cat chasing concurrently with the mouse fleeing, and then when they're done, the cat fleeing followed by the mouse chasing. I've written it down using syntax that you all know, right? Why do we deny that to the children? They need even more support than we do. I can write these automata. I don't want to, but I can. They're really much more powerless in that respect. So that's a first aspect, I think one of the first two major aspects. The second major aspect is preemption. And again, when you say it with a fancy word like that, it sounds very technical, but the idea of, you do something until someone tells you to stop, this is a very fundamental idea that the children are intimately familiar with, right? And so the problem that they might encounter to do with preemption is this idea of, well, maybe you're repeating until the cat reaches a mouse, you want your cat to move. So how does a cat move? I guess a cat moves by moving the front left leg, then the right back leg, then the front right leg, then the back left leg, right? And this is 4 steps. But if you write it like this, in a sort of transformational language, then this doesn't stop as soon as it should. If the cat reaches the mouse here, it'll still move 3 times more before stopping. So there's something that's kind of annoying there. And of course, as you well know, you can write spaghetti code that avoids this. Again, I can do that. You can do that. None of us want to do that, and the children, it's just too much, right? They'll do it wrong, they'll get fed up. And not only is it spaghetti code, but also it completely kills any form of modularity. Like if you have code that wasn't written to be preempted, you can't preempt it in these languages. You have to go and edit that code and basically edit every single line. And if a child says, oh, but I want my cat to stop immediately, and you tell them, oh, it's easy, just write this, they look at you and they go like, what is wrong with you? There's really this sort of this loss of respect, like, why are you giving me this stupid programming language? Like, why is programming so stupid? I can say in words what I want to see happen. Why can't the language do that? And the answer is, well, obviously the language can do that if you use the right language, right? So you can have a language with first-class preemption. You can introduce what some languages call a trap, and then you have your code here that moves the cat limb one by one, and then as soon as the cat touches the mouse, you just sort of suspend that computation. Wherever inside of this it was, you just immediately stop. And this, again, it's a concept that the children understand. It's a concept that the children can express, but the language denies it to them. So these are the big 2 concerns, I think. There's a bunch of other things. One of them is sort of loosely described as user-defined signals. So often when you write a program, you might have like a sprite, a cat that does something, and then a mouse that does something, and then you want to sort of link them. Maybe when the cat touches something, it should do something, and then the mouse, as soon as the cat touches that thing, it should also start doing something. So you want to have some communication between these 2 things. And again, this is a very natural notion. Children are used to being told things by people and doing them, or telling people to do things and the people do it. How do you do that in some transformational language? Well, obviously, you just write shared memory concurrency. I mean, how hard can that be, right? I mean, it's not like, most of my research career is centered around the fact that shared memory concurrency is just outrageously difficult even for experts. I mean, when you show this, like sort of message passing by hand to a school child, they're just like baffled. Like, how can this be the solution to my problem? And then, I mean, there's no hope that they can maintain this kind of program. I mean, if you show them a simple example, they might be able to copy it in their own program. But typically, you have to insert that in their program, and then as soon as they want to change anything, they have no idea what's going on. Again, first-class signals. That's a thing. I can give you some syntax for it. I can give you some semantics for it. You can define signals. You can test for presence of signals, and you can emit signals. It's clean. Plus, it supports scoping. So you can define your interaction between your things, and then sort of forget about this interaction from the outside. So it's kind of clean and modular and nice. It also means that sort of these events, they don't have to be just at the top level anymore. So it's more flexible, cleaner, and honestly much simpler. And the final thing that is sort of sore point is time. And this is a bit more of a sort of implicit problem, which is these languages often, or almost always, don't have a proper notion of time, where they have a sort of implicit notion of time. So you might imagine you might want to move an object 10 times, and you might want to do that in two ways. You might want to move it 10 times in one go, or you might want it to move 10 times, one step, then wait a little bit, then one step, then wait a little bit, and so on and so forth. And so you need to decide sort of where in your language steps of time are taken. And typically these languages sort of do that implicitly. And often they do that at the boundary between sort of sequential composition in loops. So they will say something like, if you put move right by 3 10 times, then that will take sort of 10 frames, 10 30th of a second or something like that. Whereas if you put it in a loop, then it means you sort of do it instantly 10 times, right? From one frame to the next, you've moved 10 times. Now, of course, different languages sort of pick different trade-offs, but at the end of the day, I think sort of if your language doesn't have a way to talk about time, then there is no right choice, right? If time is implicit, then you do this sort of hope for the best programming. So your language might say, if you sequence it 10 times, it's not the same as repeating it 10 times, in which case it will be annoying in some cases and okay in some others. Or you might say, well, they are equal, in which case it will be annoying in some other cases and nice in some other cases. But it's not only is it bad because it leads to counterintuitive results, but it's also confusing, especially when you're trying to teach loops, and the loop is not a sequential composition of the number of times the loop is taken. Like, this is super baffling, right? If you can't express loops in terms of simpler things, then it's just very confusing. Again, does it have to be like that? Well, no. We can have first-class time. I can add a pause instruction to my language, and then I have a very specific way of saying when these steps of time should be taken. Now, you might ask, wouldn't that be super annoying to have to put pauses everywhere? And the answer is, well, I don't think so, because you can infer it in most cases. So, for example, if you have an infinite loop, then it's pretty clear that there should be a pause somewhere inside the loop. You may as well put it at the end, right? And one of the things that's nice is with these IDE for kids, right? You can just insert the pause instruction in the right place, and then if they want to put the pause somewhere else, then they can put an explicit pause, and then you don't infer it anymore, and you just follow what they say. Right, so I've proposed syntax for all of these things. Sort of, it looks imaginary, right? So what I've proposed is sort of a language that takes sequential composition of concurrency, preemption, signaling, and time seriously. And these languages, they already exist. right? This is, from the 80s and the 90s, there's been a bunch of those. One that I've stolen the syntax of is STRL. And in a sense, I've already described STRL to you, but I can give you a sort of one-slide summary. It was designed for control systems, like a robot arm that does something in a factory. That was the aim. But if you think about it, it's kind of the same programs that the children write. It's sort of programs that don't do very complicated computations, but that really are centered around reacting to both external and internal events. And so, you can have sequential composition, you can have concurrent composition, you have loops, you have explicit pauses, which are different from doing nothing, and then you have signals that you can emit and test for the presence of, and you have traps that you can exit to do immediate preemption. And then on top of this kernel, you can, and people have, defined a ton of syntactic sugar to make sort of writing these things more nicely. And so what I've done is basically I've taken STRL and I've shoved it into Scratch, and the result I've called reactive Scratch, and it's basically, I've stolen the interface and I've just replaced sort of the execution engine in the middle, and I've added sort of the primitives that I want. So in particular, this pink color is for preemption, so I have my trap and my exit to trap that I use here in, I think, this small program that I don't remember what it is. Oh, when you press the space key, then the cat stops spinning. Something like that. And here it uses the composition of sequential composition of concurrency, of signals, and of traps to very directly express a program that would be kind of annoying to write otherwise. So that's great. Are we done? Well, not really. It's still a hypothesis, right? For me, as a PL person, this feels like a better language. It feels like a better fit. It feels like the kids should not get blocked in these ways. But maybe there's other factors that I don't understand or I didn't take into account that just mean that it doesn't really make a difference. I think another thing that's not so clear and that really needs to be driven by sort of experimentation is it's clear what to expose, sort of these primitives. It's not clear how to expose them, sort of what the surface language should be in order to be understandable by the children. So for example, STRL in fact has a whole bunch of syntactic sugar around traps so that you can define things in a sort of understandable way, because traps are a little bit counterintuitive if you do weird corner cases. And the final question is, even if you have this, how do you teach it? And this involves both developing a curriculum, but also having the people running these code clubs be able to program fluently in these languages. Whereas, I guess if it's Scratch, then it's close enough to Python that there's like millions of people who speak it. And before concluding, I'd like to make a small aside, which I think is also important, which is I think PL theory can help a lot with children learning how to program. And a sort of silly example of that is, it's well established that rapid error feedback is one of the pillars of learning. The way you learn effectively is whenever you do something wrong, you're told very fast so that a brain can adapt very quickly. And this sort of feedback loop is very important for effective learning. Now, school children typically write very small programs. I mean, they fit on a screen, right? Otherwise, it's too big for them and they kind of give up. And so lots of static analyses that could be used to analyze these programs, but that are classically seen as sort of intractable because, they have some exponential blow up or whatever, they become tractable because the programs are so small, O of 2 to the n is the same as O of 1 when n is equal to 1. So all of these things that we think are usually too expensive, we can just run them. It's fine if it takes 3 seconds if it helps the child learn, right? And so really, we need to move away from sort of efficiency of these static analyses and towards understandability and actionability. I think if you tell a child, like, no, your program is incorrect, deal with it, they're not going to take it well. If you tell them, oh, you should fix this, then they'll be much more likely to listen to you. So I think really we can do a lot to help in that direction. So to conclude, just to give a quick summary, right, I think that with the current languages that are being used to teach programming, children really hit this expressivity wall. And I think it's caused by the language. And I think we can alleviate this by moving to synchronous imperative languages like Estral. And if you're interested in talking about this, then I'm very keen on hearing your thoughts. And before I finish, I would like to thank the people who made this possible, both Cambridge Stimulus, which was this thing to get students to help in schools, and to the school children and the teachers at the school where I helped. Thank you.
So I'm curious how you think about how you're going to think about evaluating like some of the hypotheses that are kind of implicit in the proposal here. Because like one thing I've encountered when using Scratch with kids is that things that I want as a programmer are often like destructive to their ability to operate in the system. So I think a good example is I really like variables in like the scheme sense of what a variable is. That's not what Scratch has. It has global mutable state. But like trying to get a 7-year-old to program, it's much easier for them to understand global mutable state than it is to understand the kind of notion of a variable as it shows up either in algebra or in a programming language like Scheme. And a lot of the things that you're proposing here that are like, things like scope and, all sorts of things are like, in some ways, like really easy for grown-up programmers to think about, or maybe really hard for kids to think about at different ages. I'm curious both like, how do you want to go about like evaluating whether or not these things are improvements? And then also, you have any notion of like, changing the language as kids grow up and go through stages? Like the thing that is good for a 12-year-old and the thing that's good for a 7-year-old are maybe pretty different language designs. And so, I don't know, how do you think about all that?
I guess the answer is, it's a good question, meaning I don't know the answer, but I can tell you what I gave this big disclaimer because, as you said, these things that to me might seem like the solution, like, I acknowledge that, if you do sort of anything to do with humans, then things can act in very counterintuitive ways. And so this thing that I think might help might actually hinder. I think the only way is to test. Like, I think, like in anything in medicine, like, or, anything to do with humans, you just have to test. There's no way to sort of sit down and scratch your head and know. I think for scope and things like that, we can, I suspect, and again this would have to be tested, that we can come up with representations that sort of make them more palatable to children. Because in a sense, like Scratch and other languages, they're still very much prisoner of this sort of textual nature of programs. It's written and read top-down. I think, for example, concurrency is not a top-down thing, right? So you want to sort of have another dimension and exploit that other dimension. And again, you have a scope. You can have something like a bag that contains, the scope, or that conveys it in a visual way that they understand, rather than through this indirection, through textual order or something like that. I think also evaluating all of these things is very difficult because there's so many confounding factors. One of the things that stopped me from evaluating it is I wrote a prototype, but the prototype is slow. And the fact that it's slow means that if you do a head-to-head comparison, it's just completely impossible. I think another thing is just like visual appearance matters so much. Like if you get it polished visually, then it's going to dominate any other factor. And so I guess the answer is I don't know how to do good tests for this. And in a sense, I'm not the right person. I'm a PL person. This is why I want to talk to other people who know how to do these things. So I hope I have very unsatisfactorily answered your questions.
Thanks. Yeah, just a small question. I was interested in the jargon for the reactive primitives, particularly like a word like trap. I was thinking as a kid, if I was trying to make games, I saw a word like trap, I thought, oh great, I can trap my character and if he'll fall in a hole or something. So have you given any thought to what you might need to rename the primitives to?
Yes, I have thought about it a little bit, and in fact I do point out that trap is not great in the paper, because if you have a mouse and a cat and a trap, then it's pretty obvious there's going to be some cheese as well somewhere. Yeah, I think that, again, they sort of, as grown-up programmers, we would never think about these things for ourselves, right? But when you're designing these things for kids, you really need to think, like, how do you present these things in the right way? And then it's also culturally dependent, which is annoying. I mean, you might design your thing in English and be, okay, I'm done, and then someone translates it to some other language, and suddenly it's very confusing for reasons that have nothing to do with the language itself. But if you think in terms of ASTs, but the kids don't, right? So, yeah, I think it's something that we need to pay attention to.
Thanks.
Hi, Sean. Thanks for a great talk. It says a lot about my brain, I think, but when you were going through your list of, here, we would like to have parallel composition, or we'd like to have message passing, I was thinking, what this really means is the kids need to learn about operating systems, not just programming languages. So is the set of primitives that you want to add, is there a good match with the traditional operating system and processes and so on?
I'll go out on a leg and say no. Because I think many of the primitives as they are exposed right now are they really rely on the fact that the programmer has a sort of richer mental model that they can rely on. So for example, this idea of like having concurrent composition as a primitive, you could imagine using like fork and join and things like that. And it would be a little bit more flexible, but it's also, I think, much more difficult to understand. The opportunities to shoot yourself in the foot just increase. So I think it's not just about increasing the expressivity, it's also about restricting the expressivity. And as a sort of digression, I think, for example, one way to write these programs is using functional reactive programming. You can embed all of this inside of a functional language. I don't think that's the solution for children. They'll get so confused. Like this extra expressivity will just hinder them more than anything else. And I think in the same way, you want to really limit how many things they need to think about, to learn about, if that makes sense.
It does, yeah. I suppose I don't know enough about STRL to know that set of things is the right set of things. I should probably
Neither do I.
Well, I should read your paper, though, because that will make it clearer. So, thank you.
Thanks for the talk. It was very interesting. I was wondering if maybe, I guess maybe the way that you're thinking about Scratch as a language is maybe opposite to what the original designers were thinking, or what I imagine that they were thinking. So I guess when I think of Scratch, I think of it more as a tool to teach how imperative programming works, right? As opposed to a way to teach children how to make games. If that sort of makes sense, right? So the reason why they sort of have these things with like if statements, loops and stuff is because they want to teach children about if statements and loops and those sorts of things. So I happen to agree that I think it would actually be better if we taught them other things instead of imperative languages, but I'm quite biased because I'm a functional programmer and I prefer if they did something else and didn't get their brains poisoned by this imperative nonsense. But what is your sort of thinking about what do you want to be teaching the children, right? Or what is the goal, like the intended learning outcome of these, of this thing, as opposed to just what's the best way to sort of program these games?
Yeah. Again, this is a good question because I don't know the answer.
Sure.
I think there's part of the question is sort of how do you lure them in and how do you keep them in programming? And I think the thing that motivated me is really this feeling of like disappointment that I saw time and time again, and that I attributed to the problems caused by the language.
I think you're right on that, by the way.
Now, of course, there's a trade-off, right? I mean, if you keep them longer, but with a language that's maybe less connected to also languages that they might see in the future, then maybe that, sort of aspect dominates the benefit that you get by, keeping them more interested or less frustrated. I don't know. I think, it's really a thing where you have to look at do some studies and look at the actual trade-off and see, where does it cut off?
Great,
I don't think I can sit at my desk and decide.
Right, yeah, of course. No, I'd be very interested to see those results, so thank you.
This will be characteristically ill-formed. I tried it for a moment there, and I had to push run in order to try my program, and I wonder if that's a mistake, because you might want to take away the capacity for the child to write code and not run it, if you see what I mean. If you hit some of your notions of compositionality and having fragments run in, without being complete well enough, you needn't ask them to run it. You could just run it anyway, if you see what I mean.
Yes. In that respect, I think I was a little bit bound by two things. A, the way Scratch itself works, and B, the fact that I already spent way too much time on this prototype. So Scratch does have this ability of sort of live edit your code. I did not have time to replicate that kind of functionality. And it's also, I think it's a bit more complicated to do that in the context of a language like SPLASH' than Pascal-like language where you sort of have your program counter and you...
If you can force the feedback of the change and then seeing what that does, it seems very powerful.
Hello, thank you. My question might be the same, but in different words. Right, so I think the characteristic of Scratch that everyone knows is the kind of block-based syntactic editing and the idea of sort of locking the blocks together to form a sequence of actions. So do you think maybe there's a different user-friendly mode for expressing your programs for these richer semantics that you're proposing?
I don't know. When I think about a program, I think about the AST. Like, I never think... people always get obsessed about... they talk about programming languages and they're like, oh, I don't like Haskell because it uses white space indentation. And to me, that's just a bizarre statement to make. For me, I really think about the AST and, whether it uses curly braces or space or whatever, it's all the same to me. And so there's this whole area of how do you actually make a language that people like to use, and I don't know the answer because I never think about it.
Respectfully, syntax is what hits the novice programmer. And, we forget that.
So I think one thing that I mentioned that I did think about is sort of, I think concurrency should be horizontal in the same way that sequential composition is vertical.
That's nice.
I think block-based is very good because it maintains this property that your program is never syntactically ill-formed until you have variables, in which case weird things happen. I think there's a lot of space there for improvement, but I'm maybe not the right person to ask.
Right. Okay. Well, thank you very much for a very interesting talk.
Okay. Hi. One question. Are you aware of Haiti and the research around? Okay. All right.
Yes.
And related to that, I think I was wondering if you have thought about the gradual introduction of these features. As in, I imagine the kids at some point they face this wall, and then maybe you could do some analysis to pick out the features that you have here to suggest them in a way. As like, hey, maybe you could use this for solving your problem?
Yes, I think this is, in a sense, the Code Club curriculum kind of already does that. There's sort of, a simple project, slightly more complicated project, and you sort of use features incrementally. I think the idea of sort of revealing the language incrementally is, and also which are the things that you should introduce first, is very important. I think that a language like SPLASH', like the way it's defined is really the surface language is just syntactic sugar for the sort of this very, very small core. And I think there's really a whole design space that needs to be explored about what are the right primitives to start from so that you can then refine them in terms of sort of the kernel language itself that you might use as an expert. This is the extent of my thinking. I don't know how exactly you would do that. But I think it's important. Yeah.
Okay, thank you.